sklearn utils. Description: explain in detail. The scikit-learn sklearn library in Python provides a collection of utility functions, commonly referred to as utils, that offer valuable tools for data preprocessing, model evaluation, and general machine learning tasks. These utilities streamline common operations and enhance the overall efficiency of machine learning workflows. Inputs. Input 1. Explain in detail. The primary input to sklearn utils is typically a dataset, often represented as a NumPy array or a pandas data frame. This dataset contains the features-independent variables and potentially the target variable dependent variable for machine learning tasks. Input 2. Explain in detail. Depending on the specific utility function, additional inputs might be required, such as model parameters for model evaluation utilities, parameters like the model itself, the predicted labels, and the true labels might be needed. Preprocessing parameters for data preprocessing utilities. Parameters like the desired scaling method or the specific feature transformations might be specified. Outputs. Output 1. Explain in detail. The outputs of sklearn utils vary depending on the function. Common outputs include processed data. Data preprocessing utilities might return the transformed dataset after applying scaling, encoding, or other operations. Model evaluation metrics. Evaluation utilities generate metrics such as accuracy, precision, recall, F1 score, and other relevant measures for assessing model performance. Feature importance. Feature selection utilities can output the importance scores or rankings of features, helping identify the most influential variables. Steps. Step 1. Explain in detail. The steps involved in using sklearn utils typically follow a general pattern. Import the necessary utilities from sklearn. Prepare your dataset. Load, clean, and format it appropriately. Instantiate the desired utility function with any necessary parameters. Apply the utility function to the input dataset or other relevant data. Interpret and utilize the outputs generated by the utility function. Metrics. Metric 1. Explain in detail. sklearn utils themselves don't directly define metrics. Instead, they provide tools to compute and evaluate metrics. Some common metrics used in conjunction with sklearn utils include accuracy, the proportion of correctly classified instances; precision, the proportion of true positives among predicted positives; recall, the proportion of true positives among all actual positives; F1 score, the harmonic mean of precision and recall; mean squared error. MSE measures the average squared difference between predicted and actual values. Visualization plots. Visualization plot 1. Explain in detail. sklearn utils don't inherently generate visualizations. However, many of their outputs can be used to create insightful plots using libraries like matplotlib or seaborn. Examples include confusion matrix visualizes the performance of a classification model by showing the counts of true positives, true negatives, false positives, and false negatives. ROC curve plots the true positive rate against the false positive rate for different classification thresholds. Precision recall curve visualizes the trade-off between precision and recall for different thresholds. Feature importance plot shows the ranking or scores of features based on their importance in a model. Fine-tune parameters. Parameter 1. Explain in detail. Depending on the specific sklearn utility function, there might be parameters that allow for fine-tuning its behavior. For instance, a scaling utility might have parameters to control the scaling method, e.g., standardization, normalization, And feature selection utilities might have parameters to adjust the selection threshold. Uncertainty methods. Uncertainty method 1. Explain in detail. sklearn utils don't natively provide uncertainty quantification methods. However, they often serve as building blocks for uncertainty estimation techniques. For example, cross-validation methods e.g. k-fold cross-validation provided by sklearn can be used to generate multiple model predictions and estimate uncertainty by analyzing the variability in these predictions. Challenges and fixes. Challenge 1. Explain in detail data inconsistency. Inconsistent data formats, missing values, or unusual data distributions can lead to issues with data preprocessing and model training. Sample use case that resulted in challenge 1. A dataset with missing values in some features, causing problems with certain scaling methods that assume complete data. Fixes to challenge 1. Impute missing values. Use techniques like mean imputation, median imputation, or more advanced methods like KNN imputation to replace missing data. Handle categorical features. Encode categorical variables appropriately using methods like one-hot encoding or label encoding. Normalize or standardize data. Apply scaling methods like standardization or normalization to address differences in data ranges and scales. Challenge 2. Explain in detail incorrect data transformations. Applying inappropriate data preprocessing techniques or transformations can negatively impact model performance. Sample use case that resulted in challenge 2. Scaling features using standardization when normalization would be more suitable for the specific data distribution. Fixes to challenge 2. Analyze data distribution carefully. Examine the distribution of features to determine the most suitable scaling or transformation method. Experiment with different methods. Try different preprocessing techniques and evaluate their impact on model performance. Use domain expertise. Consult domain experts to understand potential data characteristics that might necessitate specific preprocessing steps. Challenge 3. Explain in detail overfitting or underfitting. Improperly tuned parameters or data preprocessing can lead to overfitting. High performance on training data but poor generalization, or underfitting. Poor performance on both training and test data. Sample use case that resulted in challenge 3. Using too many features in a model without proper feature selection can result in overfitting. Fixes to challenge 3. Regularization. Apply techniques like L1 or L2 regularization to penalize complex models and prevent overfitting. Cross-validation. Employ cross-validation techniques to evaluate model performance on unseen data and avoid overfitting. Feature selection. Select relevant features using methods like feature importance ranking or dimensionality reduction techniques. Challenge 4. Explain in detail incorrect metric selection. Choosing an inappropriate evaluation metric can misrepresent model performance. Sample use case that resulted in challenge 4. Using accuracy as the primary metric for imbalanced datasets might be misleading, as it favors models that predict the majority class well. Fixes to challenge 4. Understand the task. Clearly define the goals of your machine learning task to select the most relevant metrics. Use multiple metrics. Consider evaluating model performance using a combination of metrics to get a more comprehensive picture. Analyze the data. Examine the characteristics of the data, e.g., class imbalance, multicollinearity, to choose metrics that address potential biases. Challenge 5. Explain in detail poor model choice. Selecting an inappropriate model for the task or data can lead to suboptimal performance. Sample use case that resulted in challenge 5. Using a linear regression model for a highly nonlinear dataset. Fixes to challenge 5. Analyze data patterns. Explore the relationships between features and the target variable to choose a model that fits the data patterns. Experiment with different models. Try different model types, e.g., linear, tree-based, neural networks, and compare their performance. Consider domain knowledge. Involve domain experts to identify appropriate model types for a specific application. Challenge 6. Explain in detail computational resource constraints. Some pre-processing techniques or models might be computationally expensive, requiring significant resources. Sample use case that resulted in Challenge 6. Training a deep neural network on a large dataset might require extensive processing power. Fixes to Challenge 6. Optimize algorithms. Select efficient algorithms or use optimized libraries for computationally intensive tasks. Reduce data size. Consider techniques like data sampling or dimensionality reduction to reduce the computational load. Utilize cloud computing. Leverage cloud platforms with powerful computing resources to handle large datasets and complex models. Challenge 7. Explain in detail limited interpretability. Some machine learning models, particularly complex ones, can be difficult to interpret. Sample use case that resulted in Challenge 7. A black box model like a deep neural network might provide accurate predictions but lack insights into the decision-making process. Fixes to Challenge 7. Use interpretable models. Choose models known for their interpretability, such as linear models or decision trees. Feature importance analysis. Investigate feature importance scores to identify the most influential variables in the model. Explainability techniques. Explore explainability techniques like sharp values or LIME to provide insights into model predictions. Challenge 8. Explain in detail data leakage. Introducing information from the test set into the training data can lead to artificially inflated performance. Sample use case that resulted in Challenge 8. Using features from the test set during data preprocessing or model training. Fixes to Challenge 8. Ensure data separation. Keep training and test data strictly separate throughout the entire process. Perform data preprocessing independently. Apply preprocessing steps only to the training data and use the same steps without refitting to transform the test data. Avoid using information from the test set. Ensure that no information from the test set is used during model training or evaluation. Challenge 9. Explain in detail incorrect hyperparameter tuning. Using inappropriate hyperparameter values can significantly impact model performance. Sample use case that resulted in Challenge 9. Setting a learning rate that is too high or too low in a gradient descent algorithm. Fixes to Challenge 9. Grid search. Experiment with a range of hyperparameter values using grid search or random search techniques. Cross-validation. Use cross-validation to evaluate model performance with different hyperparameter settings. Early stopping. Monitor model performance during training and stop training when performance on a validation set starts to plateau. Challenge 10. Explain in detail lack of robustness. Models can be sensitive to small changes in the input data, leading to unpredictable behavior. Sample use case that resulted in Challenge 10. A model trained on a specific dataset might perform poorly on data with slightly different characteristics. Fixes to Challenge 10. Robust preprocessing. Employ preprocessing techniques that are robust to outliers or noisy data. Ensemble methods. Use ensemble methods like bagging or boosting to combine predictions from multiple models, reducing the impact of individual model errors. Data augmentation. Generate synthetic data variations to improve model robustness and generalization. Challenge 11. Explain in detail bias in data. Data can reflect existing biases present in the real world. leading to models that make unfair or discriminatory predictions. Sample use case that resulted in Challenge 11. A model trained on a biased dataset might perpetuate racial or gender disparities. Fixes to Challenge 11. Collect diverse data and ensure that the training data represents the diversity of the population or system you are modeling. Bias detection and mitigation. Use techniques to identify and mitigate bias in the data and model. Fairness metrics. Evaluate model performance using fairness metrics that assess the impact of a model on different groups. sklearn, utils, bunch. Description. The bunch object in scikit-learn sklearn is a simple container for data. It is essentially a dictionary-like object, but with attributes accessible by name instead of by key. This makes it easier to work with data that has multiple named attributes, such as the results of a machine learning model. Inputs: a dictionary or a set of key-value pairs. Outputs: a bunch object containing the provided data with accessible attributes. Steps: initialize a bunch object with the provided data. Access the data using dot notation, e.g. bunch object, attribute name. Metrics: no specific metrics associated with the bunch object itself. It is a data structure and not a specific algorithm. Visualization plots: not applicable. Fine-tune parameters: no tunable parameters associated with the bunch object. Uncertainty methods: not applicable. Challenges and fixes. Challenge 1: confusion with dictionary behavior. Sample use case that resulted in Challenge 1: you might accidentally try to access data using square brackets, like bunch object attribute name, which might not work as expected if the attribute is a nested structure. Fixes to Challenge 1: use dot notation bunch object, attribute name instead of square brackets for accessing attributes. Challenge 2: overwriting existing attributes. Sample use case that resulted in Challenge 2: assigning a new value to an existing attribute will overwrite the original value. Fixes to Challenge 2: avoid overwriting existing attributes by using different attribute names, though checking if an attribute already exists before assigning a new value. sklearn, utils, as float array. Description. The as float array function in scikit-learn sklearn converts input data to a NumPy array with floating point data type. It is designed to handle various input formats and ensure consistency for machine learning algorithms. Inputs: x the input data to be converted. It can be a list, NumPy array, pandas data frame, or sparse matrix. D type the desired data type for the output array. By default, it is float 64. Order the memory layout of the array. Either C row major or F column major. Default is C. Copy whether to create a copy of the input data. If false, the input data will be modified in place if needed. Force all finite if true. Check that all values are finite, not none or INF. If false, the function will pass through any non-finite values. Outputs. X out a NumPy array with floating point data type. Converted a Boolean value indicating whether the input data was converted to a new array. Steps. The function checks the input data type and performs necessary conversions to ensure it is a NumPy array. If D type is specified, the array is converted to the specified data type. If copy is true, a copy of the input data is created. Otherwise, the input data is modified in place if needed. If false, all finite is true, the function checks for non-finite values none or INF and raises an exception if found. Metrics. None directly related to as float array. However, the output array can be used for further analysis and model training, where metrics like accuracy, precision, and recall might be applicable. Visualization plots. None directly related to as float array. However, the output array can be used to visualize the data distribution using histograms. Scatter plots, etc. Fine-tune parameters. D-type allows you to specify the desired data type for the output array. Use float32 if you are concerned about memory usage or float64 for higher precision. Copy if you are dealing with large datasets and memory is a concern. Set copy false to avoid creating a copy of the input data. However, be mindful of potential modifications to the original data. Force all finite. Use force all finite true if you want to ensure that the data does not contain any non-finite values none or INF. This can help prevent errors in some machine learning algorithms. Uncertainty methods. None directly related to as float array. It's a conversion function, not an estimator that provides uncertainty measures. Challenges and fixes. Challenge 1. Input data containing non-finite values none or INF when force all finite true. Sample use case. A dataset with missing values represented as none. Fixes. Handle missing values before calling as float array by replacing them with appropriate values, e.g. mean, median, or dropping them. Use force all finite false if non-finite values are acceptable in your specific use case. Challenge 2. Input data with mixed data types, leading to potential type conversion issues. Sample use case. A dataset with columns containing both numeric and categorical values. Fixes. Convert all columns to numeric values before calling as float array. Use appropriate data encoding techniques, e.g. one-hot encoding for categorical features. sklearn utils assert all finite. Description. This function is used to check if a NumPy array contains any non-finite values, infinities or nans. It raises a value error if non-finite values are found, ensuring that your data is suitable for use with scikit-learn. Inputs. Array. The NumPy array to be checked for non-finite values. ERRMSG optional. A custom error message to be used if non-finite values are found. If not provided, a default message will be used. Outputs. None. The function does not return any value. It either raises a value error or does nothing if all values are finite. Steps. The function first checks if the input array is a NumPy array. It then uses the NumPy is finite function to check if all values in the array are finite. If any non-finite values are found, a value error is raised with the specified or default error message. Challenges and fixes. Challenge 1. Inputting an array with non-finite values. Sample use case. Assert all finite NP. Array 1. 2. NP.inf. Fixes replace the non-finite values with finite values or remove the non-finite rows or columns from the array. Challenge 2. Incorrect input type. Sample use case. Assert all finite list 1, 2, 3. Fixes convert the input to a NumPy array using NP array. sklearn utils deprecated. Description: the sklearn utils deprecated module provides tools for marking functions, classes, and methods as deprecated in scikit-learn. These tools allow developers to gradually phase out older features and guide users towards using newer and more efficient alternatives. Inputs: function, class, or method. The entity to be marked as deprecated. This could be a function, class, or method within a scikit-learn module. Deprecation message: a clear and concise message explaining why the entity is deprecated and what alternative users should consider. Version: the scikit-learn version in which the entity is scheduled for complete removal. This helps users understand when they should fully migrate to alternative solutions. Outputs: decorated entity. The input entity, function, class, or method is returned with the deprecation warning attached. This means that when the deprecated entity is used, a warning message will be issued to inform users of the deprecation. Steps: import the deprecated module from sklearn utils. Import deprecated. Use the deprecated decorator. Decorate the entity with the deprecated decorator, providing the necessary arguments. Python deprecated version 1.0. Message: this function is deprecated. Use new function instead. Def old function. Code for the old function. Execute the deprecated entity when the decorated entity is called. The deprecation warning message will be displayed. Metrics: deprecation warning coverage. The percentage of deprecated entities that are correctly decorated. And trigger warning messages. Visualization plots. None. Fine-tune parameters. Version specifies the version of scikit-learn in which the entity will be removed. Message customizes the warning message displayed when the deprecated entity is used. Extra args allows for passing additional arguments to the deprecation warning. Uncertainty methods. None. Challenges and fixes. Challenge 1: incorrectly specified deprecation version or message. Sample use case that resulted in challenge 1: a developer mistakenly used an incorrect version or provided an unclear message, leading to confusion among users about the deprecation status and alternatives. Fixes to challenge 1: ensure that the deprecation version and message are accurate and reflect the intended usage. Challenge 2: overuse or improper use of the deprecated decorator. Sample use case that resulted in challenge 2: a developer might have marked a function as deprecated without a clear plan for replacement, or might have used it for minor changes that didn't require full deprecation. Fixes to challenge 2: use the deprecated decorator judiciously. Prioritize marking features with significant changes or replacements and consider alternative approaches like warnings or informational messages for minor updates. sklearn utils estimator HTML REPR. Description: explain in detail. Estimator: a scikit-learn estimator object. This is the main input, representing a trained machine learning model. Indent: an integer representing the indentation level for the HTML output. This is used to control the visual spacing of the representation. Show feature importances: a Boolean flag determining whether to display feature importances for models that support this feature, e.g. random forest classifier. Max depth: an integer specifying the maximum depth to display for nested objects like pipelines or ensembles. This limits the level of recursion for complex models. Show dimensions, a Boolean flag indicating whether to display the dimensions of the fitted data, e.g., number of samples and features. This helps understand the input size used for training. HTML representation, a string containing the HTML representation of the estimator. This is a formatted, human-readable display of the model's parameters, hyperparameters, and other relevant information. Initialization, the function initializes an internal structure to store the HTML content. Recursive processing, it recursively traverses the estimator object, inspecting its attributes and sub-estimators. Attribute extraction, for each attribute, it determines its type and formats it appropriately. This includes handling nested structures like pipelines and feature importances. HTML construction, the function builds the HTML representation by composing various elements based on the attribute types. This includes titles, lists, tables, and indentation to ensure readability. Not directly applicable, as the function focuses on visualization and not metric computation. Not directly applicable, as the function generates a static HTML representation, not interactive visualizations. Indent, this parameter controls the indentation level, which affects the visual spacing of the HTML output. Higher values lead to deeper indentation. Show feature importances, this parameter determines whether feature importances are displayed for compatible models. Max depth, this parameter controls the maximum depth for nested objects in the representation. This helps control the complexity of the output for deeply nested models. Show dimensions, this parameter determines whether the dimensions of the fitted data are shown, providing information about the input size. Not applicable. The function is concerned with visualization, not uncertainty estimation. Challenge 1, handling complex nested objects, e.g., pipelines with nested estimators can lead to long, unwieldy HTML output. Sample use case that resulted in challenge 1, a pipeline with multiple steps, each containing their own estimators, resulting in a deeply nested structure. The max depth parameter allows limiting the depth of nested objects, preventing excessively verbose output. Challenge 2, displaying feature importances for models that don't support them could lead to errors or incorrect information. Sample use case that resulted in challenge 2, attempting to display feature importances for a model like logistic regression, which doesn't have a built-in feature importance attribute. Fixes to challenge 2, the show feature importances parameter is used to control whether feature importances are displayed. This ensures that the function only displays feature importances for models where they are applicable. sklearn, utils, gen batches. Description. The gen batches function from Scikit learns utils module is a utility for efficiently generating batches of data. It's particularly useful when working with large datasets that cannot fit entirely in memory. This function helps to split the data into manageable chunks, allowing for processing in batches without overwhelming system resources. Inputs. N samples. This input specifies the total number of samples in your dataset. It's a positive integer indicating the size of the complete dataset. Batch size. This input defines the desired size of each batch. It's a positive integer representing the number of samples to include in each batch. N batches. This input is optional, if provided. It sets the exact number of batches to generate. If not provided, the function automatically calculates the number of batches based on n samples and batch size, ensuring that all samples are included. Outputs. A generator object. This object yields batches of indices, Each batch is represented as a slice object, indicating the starting and ending indices for the current batch within the dataset. This allows you to easily access the corresponding data for processing. Steps. Calculate the number of batches. The function determines the number of batches needed to cover all samples. If n batches is provided, it's used directly. Otherwise, it's calculated by dividing n samples by batch size and rounding up to ensure all samples are included. Generate batch indices. The function iterates through the calculated number of batches. In each iteration, it creates a slice object defining the start and end indices for the current batch. The start index is calculated by multiplying the batch index with batch size. The end index is calculated by adding batch size to the start index. The slice object is then yielded to the caller. Metrics. None. The function itself doesn't directly provide any metrics, as it's primarily focused on generating batches. Metrics would typically be calculated during the data processing steps that use these batches. Visualization plots. None. The function doesn't generate any visualizations directly. Data processing steps that utilize the generated batches might involve visualizations. Fine-tune parameters. Batch size. Adjusting this parameter allows you to control the size of each batch, enabling you to balance memory usage and processing efficiency based on your computational resources. Smaller batches consume less memory but might require more iterations, while larger batches consume more memory but reduce the number of iterations. N batches. Specifying this parameter allows you to control the precise number of batches to generate. This can be useful if you have specific requirements regarding the number of batches or if you want to ensure consistent batch sizes. Uncertainty methods. None. The function does not involve any uncertainty estimations or methods. Challenges and fixes. Challenge 1. Insufficient memory for large datasets. Sample use case when working with extremely large datasets that cannot be loaded into memory entirely. Processing in batches is essential. However, if the batch size is too large, it can still lead to memory issues. Fixes. Reduce the batch size. Decrease the number of samples per batch to minimize memory consumption. This might increase the number of iterations but can prevent memory overflows. Utilize memory-efficient data structures. Employ data structures like NumPy arrays or sparse matrices, which are designed to efficiently store and manipulate large amounts of data in memory. Employ techniques like data sharding or distributed processing. Split the dataset across multiple machines or processes, allowing each to handle a subset of the data and reducing memory pressure on any single machine. Challenge 2. Uneven distribution of samples in the final batch. Sample use case when n samples is not perfectly divisible by batch size. The last batch might contain fewer samples than the rest. This can lead to inconsistencies in processing if the final batch is treated differently. Fixes. Pad the data. Add dummy samples to the dataset to make n samples perfectly divisible by batch size, ensuring consistent batch sizes. Handle the final batch separately. Implement specific logic to handle the final batch differently, accounting for its potentially smaller size. Use a different batching approach. Explore alternative batching techniques, such as random sampling or dynamic batch sizing, which might address this uneven distribution issue. sklearn, utils, Genevan slices. Description. The genuine slices function in scikit-learn is designed to divide a dataset into evenly sized chunks, or slices. This is particularly useful for tasks like parallel processing, where you want to distribute the workload across multiple cores or machines. It ensures that each slice has roughly the same number of data points. Inputs. N samples. This integer represents the total number of samples in your dataset. N slices. This integer determines the number of slices you want to divide your dataset into. Outputs. Slices. This is a generator that yields tuples. Each tuple contains two integers, a start index and an end index. These indices define the boundaries of each slice within your dataset. Steps. Calculate the slice size. The function determines the approximate size of each slice by dividing the total number of samples by the number of desired slices. Create slices based on the calculated slice size. The function generates a sequence of tuples representing the start and end indices for each slice. It ensures that all slices have roughly the same size, except for the last slice, which might be slightly smaller if the total number of samples is not perfectly divisible by the number of slices. Metrics. Slice size. This metric measures the approximate number of samples within each slice. It can be calculated by dividing the total number of samples by the number of slices. Visualization plots. None. Fine-tune parameters. N slices. This parameter controls the number of slices generated. Increasing this value results in smaller slices. Uncertainty methods. None. Challenges and fixes. Challenge 1. Uneven slice sizes. If the total number of samples is not perfectly divisible by the number of slices, the last slice might be smaller than the others. Sample use case that resulted in challenge 1. If you have 100 samples and want to create 3 slices, the first 2 slices will have 33 samples each, while the last slice will have 34 samples. Fixes to challenge 1. The function inherently accounts for this by making the last slice slightly larger. This behavior is intentional and expected. Challenge 2. None. Sample use case that resulted in challenge 2. None. Fixes to challenge 2. None. sklearn utils indexable. Description. The sklearn utils indexable function is a crucial utility in scikit-learn that helps ensure data consistency and efficient handling of data transformations. It essentially facilitates the consistent mapping between the original data indices and the indices of the transformed data, particularly when dealing with transformations that may change the shape or ordering of the data. This is especially important for situations where you need to preserve the relationship between the original data and its transformed version, such as when applying machine learning models to the transformed data. Inputs. X. The input data. Typically a NumPy array or a pandas data frame representing the features or independent variables. Y. Optional. The target variable dependent variable, often a NumPy array or a pandas series. This is used in cases where the target variable also needs to be transformed or indexed along with the features. Outputs. X out the transformed input data, potentially with a modified shape or order. Y out the transformed target variable, if provided. Steps. Index mapping. The function first determines the mapping between the original indices of the input data X and the indices of the transformed data X out. This is essential for maintaining the relationship between the original data and the transformed data. Data transformation. The provided transformer is then applied to the input data X and potentially to the target variable Y, if it is provided. Index alignment. The function ensures that the indices of the transformed data are aligned with The original indices, enabling consistent access and interpretation of the results. Metrics. Accuracy of index mapping. The precision of the index mapping is crucial for reliable data analysis. Ensure that the mapping accurately reflects the changes introduced by the transformer. Visualization plots. Scatter plots visualizing the relationship between the original and transformed data using scatter plots can help understand the impact of the transformation. Fine-tune parameters. Transformer. The choice of the transformer is fundamental to the overall outcome. Choose a transformer that aligns with the specific data transformation you require. Index handling. Understanding the specific indexing behavior of the chosen transformer is crucial. Some transformers may introduce changes to the indices, while others may maintain the original indices. Uncertainty methods. Out-of-sample performance. Evaluating the performance of the transformed data on a held-out test set can help assess the generalizability of the transformations. Challenges and fixes. Challenge 1. Inconsistent indexing. If the transformer significantly modifies the indices of A data, it can lead to mismatches and errors during subsequent analysis. Sample use case that resulted in challenge 1. Using a transformer that removes or reorders rows in the input data. Fixes to challenge 1. Carefully choose a transformer that aligns with your index handling requirements. Consider using transformers that preserve the original indices. Manually adjust indices after transformation if necessary. Challenge 2. Data loss. Certain transformations, such as feature selection, can lead to the loss of data. Sample use case that resulted in challenge 2. Applying a feature selection method that removes irrelevant features. Fixes to challenge 2. Ensure that the chosen transformer is suitable for the specific data analysis task and does not result in undesirable data loss. Consider alternative transformation methods that minimize data loss. Record the indices of the removed data points for potential later analysis. sklearn, utils, murmur 332. Description. This function is a fast and efficient hash function used to generate a 32-bit hash value for a given input. Murmur 3 is a non-cryptographic hash function known for its speed and distribution quality. Inputs. Key. The input data to be hashed can be any hashable Python object like string, tuple, list. Seed. An integer value used as an initial seed for the hash function. It helps to improve the randomness of the hash values. Outputs. Hash value. A 32-bit integer representing the hash value of the input key. Steps. The function iterates through the input key, processing each byte to generate a hash value. It uses a series of bitwise operations, rotations, and multiplications to create a unique hash value. The seed value is used as the initial state for the hash function, ensuring a unique hash output for different seeds. Metrics. Collision rate. It measures how often different inputs produce the same hash value. A low collision rate is desirable. Distribution. It measures how evenly the hash values are distributed across the output range 0 to 232 to 1. An even distribution indicates better hash function performance. Visualization plots. Histogram of hash values. This plot shows the frequency distribution of the hash values generated for a set of inputs. Collision probability plot. This plot shows the probability of collisions for different numbers of inputs. Fine-tune parameters. Seed. The seed value can be adjusted to change the initial state of the hash function, influencing the hash values. Uncertainty methods. None, as it is a deterministic function. There is no inherent uncertainty in the output. Challenges and fixes. Challenge 1 collisions. It is possible for different inputs to generate the same hash value, though the probability is relatively low. Sample use case that resulted in challenge 1. 2 different strings, hello and world, might produce the same hash value. Fixes to challenge 1. Use a stronger hash function like SHA-256 if a lower collision probability is needed for cryptographic purposes. However, this would be slower. Challenge 2. Limited output range. The output range is limited to 32 bits, which might not be sufficient for larger datasets with a high probability of collisions. Sample use case that resulted in challenge 2. When hashing a large number of distinct inputs, the chances of collisions increase due to the limited output range. Fixes to challenge 2. Use a larger hash function like murmur hash 3128 or a cryptographic hash like SHA-256. sklearn, utils, resample. Description. The resample function from Scikit learns utils module provides a convenient way to perform various resampling techniques on data, enabling tasks like bootstrapping, subsampling, and creating balanced datasets. Inputs. Array. The input array or sequence containing the data to be resampled. It can be a 1D array, a 2D array representing samples as rows and features as columns, or a list of arrays. Replace. A Boolean value indicating whether to sample with replacement. If true, the same element can be selected multiple times. If false, each element can be selected only once. N samples. The desired number of samples to be drawn from the input data. Random state. An integer value or none. It specifies the random number generator seed for reproducibility. If none, the random number generator is initialized with the current system time. Stratify. An array-like object containing the labels or group identifiers for stratified sampling. If provided, the function ensures that the proportions of each group in the resampled data remain consistent with the original data. Outputs. Array. The resampled array with the specified number of samples n samples. The shape of the output array depends on the shape of the input array. Steps. The function first initializes a random number generator based on the random state parameter. If stratify is provided, it performs stratified sampling, ensuring that the proportions of each group are preserved in the resampled data. The function then draws samples from the input array based on the replace and n samples parameters. If replace is true, samples are drawn with replacement, allowing the same element to be selected multiple times. If replace is false, samples are drawn without replacement, ensuring that each element is selected at most once. Metrics. The effectiveness of resampling techniques is typically evaluated based on the performance of subsequent models trained on the resampled data. Common metrics include accuracy, the percentage of correctly classified samples; precision, the proportion of positive predictions that are actually positive; recall, the proportion of actual positive cases that are correctly identified; F1 score, the harmonic mean of precision and recall. Visualization plots. Scatter plots can be used to visualize the distribution of data before and after resampling, particularly when dealing with two-dimensional data. Histograms can be helpful to visualize the distribution of features in the original and resampled datasets. Fine-tune parameters. Replace. Adjusting the value of replace allows you to control whether to perform sampling with or without replacement. This can impact the variance of the resampled data. N samples. The N samples parameter determines the size of the resampled dataset. Varying this parameter allows you to create datasets of different sizes. Stratify. The stratify parameter enables stratified sampling, which is crucial when working with imbalanced datasets or when you want to preserve the proportions of different groups in the resampled data. Uncertainty methods. Bootstrap aggregating bagging is a common uncertainty estimation technique that uses multiple resampled datasets to create an ensemble of models. The variance of the ensemble predictions provides an estimate of the model's uncertainty. Challenges and fixes. Challenge 1. Imbalanced datasets. When working with datasets where certain classes are significantly underrepresented, resampling techniques like oversampling or undersampling can be used to create a more balanced dataset. Sample use case that resulted in Challenge 1. A dataset with 90 samples belonging to class A and 10 belonging to class B. Fixes to Challenge 1. Oversampling. Replicate the minority class samples class B to create a balanced dataset. Undersampling. Remove samples from the majority class A to achieve a balanced representation. Challenge 2. Overfitting. Resampling can sometimes lead to overfitting, especially when using techniques like oversampling. Overfitting occurs when the model learns the training data too well and fails to generalize to new data. Sample use case that resulted in Challenge 2. A model trained on an oversampled dataset might perform exceptionally well on the training data but poorly on unseen data. Fixes to Challenge 2. Regularization techniques. Use regularization techniques e.g. L1 or L2 regularization to prevent overfitting by penalizing complex models. Cross-validation. Perform cross-validation to evaluate the model's performance on unseen data and identify potential overfitting. Challenge 3. Bias in resampling. Resampling methods can introduce bias if not used carefully. For example, random undersampling might remove important information from the dataset. Sample use case that resulted in Challenge 3. Randomly undersampling a dataset might remove important samples that are crucial for the model's learning. Fixes to Challenge 3. Stratified sampling. Use stratified sampling to ensure that the proportions of different groups in the resampled dataset are representative of the original data. Adaptive resampling techniques. Explore adaptive resampling techniques that adjust the sampling process based on the characteristics of the data. sklearn utils safe indexing. Description. The safe indexing function in scikit-learn sklearn is a utility function used for safely indexing arrays and lists with potentially non-contiguous indices. It is designed to handle cases where the indexing process might result in unexpected behavior or errors, particularly when dealing with multidimensional arrays and sparse matrices. Inputs: X, the array or list to be indexed. This can be a NumPy array, a pandas data frame, a sparse matrix, or any other object that supports indexing. Indices: the indices to use for indexing. This can be a list, an array, or a slice object. Outputs: indexed array or list, the result of indexing X using the provided indices. Steps: check data type. The function first checks the data type of X. If X is a sparse matrix, it uses the appropriate indexing methods for sparse matrices. Handle non-contiguous indices. If indices is not a contiguous range, the function iterates over indices and extracts the corresponding elements from X, ensuring that the output maintains the original data structure. Handle negative indices. If indices contains negative values, they are interpreted as relative indices from the end of the array. Handle duplicate indices. If indices contains duplicate values, The corresponding elements are repeated in the output. Challenges and fixes. Challenge 1: indexing with non-contiguous indices might lead to unexpected behavior or errors, especially when dealing with multidimensional arrays or sparse matrices. Sample use case that resulted in challenge 1: indexing a 2D array with a list of non-contiguous row indices might result in a flattened array instead of a sub-array with the desired rows. Fixes to challenge 1: the safe indexing function handles non-contiguous indices by iterating over them and extracting the corresponding elements from X, ensuring that the output maintains the original data structure. Challenge 2: indexing with negative indices might cause errors if the array is not large enough to accommodate the negative offset. Sample use case that resulted in challenge 2: indexing a 5-element array with an index of -6 would raise an index error. Fixes to challenge 2: the safe indexing function handles negative indices by interpreting them as relative indices from the end of the array, ensuring that the indexing operation is always performed within the array bounds. sklearn utils safe mask. Description: the safe mask function in scikit-learn is a utility function designed to handle Boolean indexing safely in the context of data manipulation and processing. It ensures that the resulting mask is compatible with the shape and structure of the data being indexed. Inputs: X. This is the input array or data structure that will be indexed using the mask. It can be a NumPy array, pandas data frame, or any other object that supports Boolean indexing. Mask: this is a Boolean array or sequence that represents the mask to be applied to the input data. It should have the same length or number of elements as the first axis rows of X. Outputs: safe mask: this is the resulting Boolean mask, adjusted to be compatible with the input data X. It has the same shape as the first axis of X. Steps: check if X is a NumPy array. If X is a NumPy array, the function directly uses the provided mask as the safe mask. Check if X is a pandas data frame. If X is a pandas data frame, the function uses the provided mask to select rows from the data frame and returns a Boolean array of the same length as the data frame. Handle other data types for other data types. The function raises a value error to indicate that the input data type is not supported. Metrics: NA. Visualization plots: NA. Fine-tune parameters: NA. Uncertainty methods: NA. Challenges and fixes. Challenge 1: sample use case attempting to index a NumPy array with a mask that has a different length than the array's first axis. Fixes: the function raises a value error to indicate that the mask is not compatible with the data shape. Challenge 2: sample use case attempting to index a pandas data frame with a mask that has a different length than the data frame's number of rows. Fixes: the function raises a value error to indicate that the mask is not compatible with the data shape. sklearn utils safesca. Description: the safesca function in scikit-learn sklearn is designed to calculate the squared value of an input while handling potential numerical issues, specifically preventing overflow and ensuring consistent results. Inputs: X. The input value for which the squared value needs to be calculated. This input can be a single number or a NumPy array. Outputs: the squared value of the input X. This output will be a single number or a NumPy array, matching the shape of the input X. Steps: if the input X is a NumPy array, the function will iterate through each element of the array and calculate the squared value individually. For each element in X, the function will perform the following: Calculate the absolute value of the element a b as x. Calculate the square of the absolute value a b as x2. If the squared value exceeds a predefined threshold NP, finfox, dtype.max, it will clip the result to the maximum value of the data type to avoid overflow. Metrics. None. The function doesn't have specific metrics associated with its output. Visualization plots. None. There are no inherent visualization plots specific to this function. Fine-tune parameters. None. The safesca function doesn't have any parameters that can be adjusted or fine-tuned. Uncertainty methods. None. The safesca function is a deterministic operation and doesn't involve any uncertainty or probabilistic methods. Challenges and fixes. Challenge 1. Overflow. Sample use case when dealing with very large numbers. Calculating their squares can lead to values exceeding the maximum representable value for the data type, resulting in overflow. Fixes. The function mitigates this issue by clipping the squared value at the maximum representable value of the data type, preventing overflow. Challenge 2. Handling negative values. Sample use case squaring negative numbers can lead to unexpected results if not handled properly. For example, the square of -5 should be 25. But some implementations might produce a different result due to rounding errors or data type limitations. Fixes. The function uses the ABS function to ensure that the calculation is performed on the absolute value of the input, guaranteeing a positive result. This approach ensures consistency and avoids any issues with negative values. sklearn, utils, shuffle. Description. The sklearn, utils, shuffle function is a utility function within the Scikit-learn library. It's designed to randomly shuffle the elements of a sequence, array, or list while maintaining the alignment between corresponding elements in multiple sequences. Inputs. X. This is the primary input, which can be a sequence e.g. list, tuple, an array e.g. numpy array, or a pandas data frame. It represents the data to be shuffled. Y. This is an optional input, often used to represent labels or target values associated with the elements in X. It should have the same length as X. If provided, it's shuffled in the same way as X, ensuring that the correspondence between data points and their labels is maintained. Random state. This parameter controls the randomization process. It can be an integer, a random state instance, or none. Integer. A specific integer value is used as a seed for the random number generator, ensuring reproducibility. Random state instance. An instance of random state from NumPy is used to manage the random number generator. This allows for finer control and potential customization. None. If random state is none, the random number generator is seeded using the system's clock, making the results less reproducible but more unpredictable. Outputs. X. The shuffled version of the original input X. The data points or rows are rearranged randomly. Y. If provided, this is the shuffled version of the input Y. It will be shuffled in the same way as X, maintaining the pairing of data points and labels. Steps. Random number generation. The function uses a random number generator controlled by random state to generate a sequence of random numbers. Shuffling. The random numbers are used to create a permutation of the indices of the input data. The data is then rearranged based on this permutation. Alignment preservation. If Y is provided, the same permutation of indices is applied to both X and Y, ensuring that the relationship between them remains intact. Metrics. Not directly applicable. sklearn, utils, shuffle is a preprocessing step. and it doesn't directly involve the calculation of metrics like accuracy or precision. Its main role is to randomize data. Visualization plots. Not directly applicable visualization plots are usually related to model outputs or data. Exploration. Not the shuffling process itself. Fine-tune parameters. Random state. This parameter controls the randomness. Setting a specific integer value allows you to reproduce the same shuffling order across runs. Using none, the default or a random state instance results in different shufflings every time. Uncertainty methods. Not directly applicable. The function doesn't involve any probabilistic models or uncertainty. Estimation. Challenges and fixes. Challenge 1. Unintentional data leakage. Sample use case. If shuffling is applied to data before splitting into training and testing sets, information from the test set might leak into the training set, potentially impacting the model's performance. Fixes. Apply shuffling after splitting the data into training and testing sets. Use sklearn, model selection, train test split, which includes shuffling as an optional parameter. Challenge 2. Reproducibility. Sample use case. When using none for random state, the shuffling order will vary each time you run the code. This makes it harder to replicate experiments. Fixes. Set a specific integer value for random state to guarantee the same shuffling order across runs, ensuring reproducible results. sklearn utils validation. Description. Explain in detail the sklearn utils validation module in scikit-learn provides a set of functions for validating and preprocessing data before feeding it to machine learning models. It helps ensure that your data is in the correct format and meets certain criteria, preventing unexpected errors and improving model performance. Inputs. Input 1. Explain in detail data. This is the input data that needs to be validated and preprocessed. It can be a NumPy array, pandas data frame, or any other data structure that can be converted to a NumPy array. Input 2. Explain in detail parameters. This may include specific parameters like estimator, the machine learning model you plan to use. D-type, the desired data type for the input features. Ensure 2D, whether to ensure that the input data is a 2D array. Allowed, whether to allow multidimensional arrays. Force all finite, whether to raise an error if the input data contains non-finite values none or INF. Outputs. Output 1. Explain in detail validated and preprocessed data. The output is the transformed data that is now in a suitable format for your machine learning model. Output 2. Explain in detail potential warnings or errors the validation functions may raise. Warnings or errors if they detect issues with the data, helping you identify and address problems before training your model. Steps. Step 1. Explain in detail data type. Checking ensures that the data is of the specified data type or can be converted to the desired data type. Step 2. Explain in detail dimensionality. Checking validates that the data has the correct number of dimensions, e.g., a 2D array for most machine learning models. Step 3. Explain in detail handling missing values. Allows you to specify how to handle missing values, e.g., impute them, drop rows, columns, raise an error. Step 4. Explain in detail. Checking for infinities and nans ensures that the data does not contain infinite values, INF, or not a number nan values, which can cause issues with many machine learning algorithms. Step 5. Explain in detail scaling and normalization. Optionally, you can apply scaling and normalization to the data to bring all features to a similar scale. Metrics. Metric 1. Explain in detail. There are no specific metrics directly associated with validation. But the effectiveness of validation can be indirectly measured by model performance on unseen data. Validation can lead to more robust models that generalize well to new data. Reduction in errors and warnings during training. Validation helps prevent errors and unexpected behavior during model training. Metric 2. Explain in detail. None. Visualization plots. Visualization plot 1. Explain in detail. There are no specific visualizations directly related to validation. However, you can use visualizations to explore your data before and after validation to assess the impact of pre-processing steps. Visualization plot 2. Explain in detail. None. Fine-tune parameters. Parameter 1. Explain in detail. D type specifies the desired data type for your input features. Parameter 2. Explain in detail. Ensure 2D determines whether the input data should be a 2D array. Parameter 3. Explain in detail. Alone allows you to specify whether to permit multidimensional arrays. Parameter 4. Explain in detail. Force all finite enforces the requirement that the data should not contain any non-finite values, none or INF. Uncertainty methods. Uncertainty method 1. Explain in detail. There are no uncertainty methods specifically tied to validation. However, after validation, you can apply uncertainty methods to your trained model to assess its confidence in predictions. Uncertainty method 2. Explain in detail. None. Challenges and fixes. Challenge 1. Explain in detail. Data type mismatch. The input data may not have the expected data type. Sample use case that resulted in challenge 1. You might be passing a pandas data frame with columns of mixed data types, e.g., strings and integers, to a model that expects all features to be numeric. Fixes to challenge 1. Use the asType method to convert the data to the desired data type. You can also use the sklearn, utils, validation, checkarray function to enforce data type consistency. Challenge 2. Explain in detail. Incorrect dimensionality. The data may not have the correct number of dimensions, e.g., 2D array for most models. Sample use case that resulted in challenge 2. You might be providing a 1D array, a vector, to a model that expects a 2D array, a matrix. Fixes to challenge 2. Reshape the data to the appropriate dimensions. You can use the reshape function in NumPy to achieve this. You can also use the sklearn, utils, validation, checkarray function with the ensure 2D parameter set to true. Challenge 3. Explain in detail. Missing values. The data may contain missing values, none. Sample use case that resulted in challenge 3. Your dataset may have missing values in some columns, which could cause problems during training. Fixes to challenge 3. Handle missing values using strategies like imputation. Replace missing values with estimated values using techniques like mean imputation, median imputation, or more sophisticated methods. Dropping rows, columns. Remove rows or columns containing missing values. Use models that can handle missing values. Some models, like decision trees, can handle missing values directly. Challenge 4. Explain in detail. Non-finite values, INF. None. The data may contain infinite or none values. Sample use case that resulted in challenge 4. You might encounter cases where calculations result in infinite values or none values, which can disrupt training. Fixes to challenge 4. Identify and remove non-finite values. Use functions like np, isna and np, isenf to detect these values and remove them or replace them with appropriate values. Pre-process data to prevent non-finite values. Consider scaling or normalization techniques that might help prevent these issues. Use models that can handle non-finite values. Some models, like decision trees, can handle non-finite values to some extent. sklearn, utils, checkexe. Description. The checkexe function in scikit-learn sklearn is a utility function used to validate the input data X and target labels Y before feeding them into an estimator model. It ensures that the data is in the correct format and meets the assumptions required by most estimators. Inputs. X, the input data. It can be a NumPy array, pandas data frame, or other formats compatible with scikit-learn. It represents the features or independent variables. Y, the target labels or dependent variables. It can be a NumPy array, pandas series, or another compatible format. Outputs. X, the validated input data, potentially converted to a NumPy array. Y, the validated target labels, potentially converted to a NumPy array. Steps. Data type check verifies if X and Y are instances of allowed data types NumPy arrays. Pandas data frames, etc. Data shape check validates if the data has the expected dimensions and shape. For instance, X should have a two-dimensional shape, number of samples, number of features, while Y can be a one-dimensional array representing the labels. Missing value check detects and potentially handles missing values nans based on the accepts pass. And force all finite arguments. Data conversion converts the input data to the required format, typically NumPy arrays. Metrics. None. This function doesn't compute any specific metrics. Its purpose is to ensure data quality. Visualization plots. None. This function does not produce visualizations. Fine-tune parameters. Accept sparse Boolean whether sparse matrices are accepted. Default is false. Force all finite Boolean whether to raise an error if X or Y contains infinities or nans. Default is true. D-type data type to convert X and Y to. If none, the data types are preserved. Order whether X and Y should be forced to be in C or Fortran order. Default is none. Copy Boolean whether a copy of X and Y is made. Default is true. Check D-type Boolean whether to check that the data type of X and Y is acceptable. Default is true. Estimator. The estimator that will use the data. This can be used to check if the data is suitable for the estimator. Default is none. Uncertainty methods. None. This function does not offer uncertainty quantification. Challenges and fixes. Challenge 1. Input data contains invalid data types. Sample use case that resulted in challenge 1 passing a list instead of a NumPy array for X. Fixes to challenge 1. Convert the list to a NumPy array before passing it to checkexe. Challenge 2. Input data has incorrect dimensions. Sample use case that resulted in challenge 2. X has a one-dimensional shape instead of a two-dimensional shape. Fixes to challenge 2. Reshape X to the required two-dimensional shape. Challenge 3. Input data contains missing values nans. Sample use case that resulted in challenge 3. X has missing values that were not handled properly. Fixes to challenge 3. Impute the missing values using a suitable method. Or set force all finite to false to allow nans. Challenge 4. Input data has inconsistent data types. Sample use case that resulted in challenge 4. X has a mix of numerical and categorical features, while Y is a string array. Fixes to challenge 4. Convert all data to a consistent data type, either numerical or categorical, using appropriate methods like astype or one-hot encoding. sklearn, utils, checkarray. Description. The checkarray function from scikit-learn sklearn is a utility function designed to ensure that input data to various scikit-learn estimators like classifiers, regressors, etc. is in a format suitable for processing. It checks the input array for conformity to expected data structures and performs necessary Conversions or raises errors if the input is invalid. Inputs. Array. The input array-like object. This could be a NumPy array, a list, a pandas data frame, or a similar structure. Except sparse, a Boolean flag indicating whether sparse matrices are acceptable as input. Except large, sparse, a Boolean flag indicating whether large sparse matrices are acceptable. Depending on the size of the array, the function might convert them to dense. D-type, the desired data type for the input array. If not specified, the function tries to infer it from the input. Order specifies the desired memory layout of the array. C for C contiguous row major or F for Fortran contiguous column major. Copy, a Boolean flag determining whether the input array should be copied. Setting it to true ensures that the original array remains unmodified. Force all finite, a Boolean flag that determines whether to enforce all values in the array to be finite, not none or infinity. If true and a value is found to be non-finite, a value error is raised. Ensure 2D, a Boolean flag that controls whether the input array should be reshaped into a 2D array. If true, 1D arrays will be reshaped into a 2D array with a single column. Allowed, a Boolean flag that indicates whether multidimensional arrays more than 2 dimensions are allowed as input. Ensure min samples, an integer specifying the minimum number of samples rows required in the input array. Ensure min features, an integer specifying the minimum number of features columns required in the input array. Estimator, the name of the estimator optional. This is used to provide a more informative error message if the input array is not valid. Outputs. Array, the modified input array, ensuring it conforms to the specified requirements. Warning, a list of warnings encountered during the check, such as D-type mismatches or other issues. Steps. Type checking, the function checks the type of the input. It should be a NumPy array, list, pandas data frame, or a similar array-like structure. Sparsity handling, if sparse matrices are acceptable except sparse is true, the function handles them appropriately. If not, it attempts to convert them to dense matrices. Data type conversion, if a specific data type D-type is specified, the function tries to convert the input to that type. Shape validation, the function enforces the desired shape of the input array. For example, it ensures that the array has the minimum number of samples and features specified. Finite values, if force all finite is set to true, the function checks whether the array contains any non-finite values, none or infinity, and raises an error if found. Metrics, not applicable. Visualization plots, not applicable. Fine-tune parameters, except sparse, control whether sparse matrices are acceptable as input. D-type, specify the desired data type for the input array. Ensure 2D, ensure that the input array is reshaped into a 2D array. Allowed, allow multidimensional arrays more than 2 dimensions as input. Ensure min samples, specify the minimum number of samples rows required. Ensure min features, specify the minimum number of features columns required. Uncertainty methods, not applicable. Challenges and fixes. Challenge 1, input data with incorrect data types. Sample use case that resulted in challenge 1, a NumPy array containing strings instead of numeric values for a regression model. Fixes to challenge 1, specify the correct D-type parameter in check array, e.g. D-type float to convert the data to the appropriate type. Challenge 2, input data with inconsistent dimensions. Sample use case that resulted in challenge 2, a list containing arrays with different lengths. Fixes to challenge 2, ensure the input data has consistent dimensions by padding or truncating the arrays to match the desired length. Challenge 3, input data containing non-finite values, none or infinity. Sample use case that resulted in challenge 3: an array containing non-values, which are not acceptable for many scikit-learn models. Fixes to challenge 3 handle non-finite values by either replacing them with a specified value, e.g., the mean of the column, removing rows or columns with non-finite values, or raising an exception. Challenge 4: input data in the wrong format, e.g., a list instead of a NumPy array. Sample use case that resulted in challenge 4: passing a list of lists directly to a scikit-learn model that expects a NumPy array. Fixes to challenge 4: convert the input data to a NumPy array using functions like np array. Challenge 5: input data with a sparse format that is not supported. Sample use case that resulted in challenge 5: using a sparse matrix with a format not supported by the scikit-learn model. Fixes to challenge 5: ensure that the sparse matrix format is supported by the scikit-learn model, or convert the sparse matrix to a different format. sklearn, utils, checkscaler. Description: the checkscaler function in scikit-learn sklearn is a utility function used to validate that a given input is indeed a scalar value. It plays a crucial role in ensuring data integrity and consistency within machine learning pipelines, especially when dealing with model parameters or data transformations. Inputs: x, the input value to be checked. This can be any Python object. D type, the expected data type of the scalar. If not provided, it defaults to none, meaning any data type is accepted. You can specify specific data types like int, float, str, etc. Target type specifies the expected type of the input. It can be numeric for numerical values, str for strings, or bool for booleans. Float kind optional, the float kind, such as float 64 or float 32, to be checked. If not specified, the function will accept any floating point type. Int kind optional, the integer kind, such as int 64 or int 32, to be checked. If not specified, the function will accept any integer type. Outputs: returns the input value x if it passes the validation checks. Raises a value error if the input is not a scalar or if it fails to meet the specified data type or target type requirements. Steps: type checking. The function first checks the type of the input value x. If the input is not a scalar, i.e., it's a list, tuple, dictionary, or another complex object, it raises a value error. Data type checking: if a D type is provided, the function verifies if the input's data type matches the specified D type. If not, it raises a value error. Target type checking: if a target type is provided, the function ensures that the input's type corresponds to the specified target type, e.g., numeric, str, or bool. If not, it raises a value error. Floating point and integer type checking: if float kind or int kind is provided, the function checks if the input is of the specified floating point or integer kind, respectively. If not, it raises a value error. Metrics: data validation: the primary metric is the successful validation of the input as a scalar meeting the specified criteria. A successful validation means that the input is a scalar and meets the data type, target type, and if applicable floating point or integer kind requirements. Visualization plots: data type distribution: you can visualize the data type distribution of the input values to identify potential inconsistencies or unexpected types. This can help in understanding the nature of your data and potentially debug issues related to data type mismatch. Fine-tune parameters: D-type: the D-type parameter allows you to specify the expected data type of the input scalar, enforcing stricter data validation. Target type. The target type parameter enables you to define the expected type of the input, further refining the validation process. Float kind, int kind. The float kind and int kind parameters provide fine-grained control over acceptable floating point and integer types, respectively. Uncertainty methods. Type inference. The checkscaler function uses type inference to determine the type of the input. However, this inference can sometimes be ambiguous or inaccurate, especially for complex objects. If you have doubts about the accuracy of type inference, it's essential to provide explicit D-type or target type parameters. Challenges and fixes. Challenge 1. Incorrect type inference. Sample use case that resulted in challenge 1. You might have a variable containing a string that represents a number, like 1.2. Type inference might consider this as a string, but you might intend it to be a floating point number. Fixes to challenge 1. You can use the D-type parameter to explicitly specify the expected data type, ensuring that the string is interpreted as a float. For example, checkscaler, D-type float. Challenge 2. Unexpected input. Sample use case that resulted in challenge 2. Your code might receive a list, tuple, or other non-scalar objects as input instead of a single scalar value. Fixes to challenge 2. Review your code carefully to identify the source of the non-scalar input. Ensure that the data you are passing to checkscaler is indeed a scalar value. If necessary, modify your code to handle and convert the input to a scalar if it's a non-scalar object. sklearn, utils, check consistent length. Description. This function checks if the input arrays or sequences have consistent lengths. It's a crucial utility in scikit-learn for ensuring that data used in various machine learning models is correctly aligned and compatible. Inputs. Arrays. A list or tuple of arrays or sequences whose lengths are to be compared. Each element can be a 1D array, a list, or any object with a length attribute. Allow empty. A Boolean value indicating whether to allow empty arrays with length 0. If set to false, all arrays must have at least one element. Outputs. None. The function does not return a value directly. Instead, it raises a value error if the lengths are inconsistent, preventing further processing with mismatched data. Steps. Loop through the provided array's input. For each array, determine its length using the len function. Compare the length of the current array with the length of the first array. If any length mismatch is detected, a value error is raised, indicating that the input arrays have inconsistent lengths. Metrics. Length consistency. This is the primary metric, gauged by the successful execution of the function without raising a value error. If the function runs without error, it implies the inputs have consistent lengths. Fine-tune parameters. Allow empty. This parameter allows for flexibility in handling empty arrays. Setting it to true permits empty arrays in the input list, while setting it to false enforces non-empty arrays. Challenges and fixes. Challenge 1. Inconsistent lengths in input arrays. Sample use case. If you attempt to fit a model with features and target variables that have differing numbers of samples, this inconsistency will lead to errors. For instance, fitting a linear regression model on features with 100 samples and a target variable with 90 samples will raise an error. Fixes ensure that all input arrays have the same length before feeding them to the model or any sklearn function. Use data manipulation techniques like slicing, padding, or removing extra samples to align the lengths of all arrays. Challenge 2. Empty arrays not allowed. Sample use case when working with datasets that might have missing data. Empty arrays can occur If allowEmpty is set to false, and an empty array is present, a value error will be raised, halting the process. Fixes: examine the cause of the empty arrays. If they are due to missing data, consider imputing values using methods like mean imputation or k-nearest neighbors. Alternatively, if empty arrays are intentional, set allowEmpty to true. sklearn, utils, check random state. Description: this function is used to create a random number generator (RNG) object that can be used to generate random numbers in scikit-learn. It handles different input types for the random state to ensure consistent and reproducible results. Inputs: random state. It can be an integer, a random state instance, a none value, or NP, random state instance. If random state is an integer, it is used to seed the random state instance. If random state is a random state instance, it is used directly. If random state is none, it uses the random state instance used by NP, random. Outputs: random state. It returns a random state object. It is an instance of NumPy, random state, and ensures reproducible results. Steps: check the type of the random state input. If random state is an integer, create a new random state instance seeded with the integer. If random state is a random state instance, return the input directly. If random state is none, return the random state instance used by NP, random. Metrics: reproducibility. The function ensures that the same random state input consistently produces the same sequence of random numbers. Randomness. The generated random numbers should follow a uniform distribution and exhibit statistical randomness. Visualization plots. Histogram of random numbers visualizes the distribution of generated random numbers to confirm its uniformity. Scatter plot of random numbers visualizes the relationship between consecutive random numbers to check for any patterns or dependencies. Fine-tune parameters. Random state. Adjusting the random state integer value allows you to control the specific sequence of random numbers generated. Uncertainty methods. Bootstrap. Resampling with replacement from the generated random numbers can be used to estimate uncertainty in the output. Challenges and fixes. Challenge 1. Using different random state values in different parts of the code can lead to inconsistencies in results. Sample use case. Training a model with one random state and using a different random state for generating random features might lead to inconsistent model performance. Fixes. Use the same random state value for all relevant steps involving randomness. Utilize a common seed for all random number generators within the code to maintain consistency. Challenge 2. The default random state instance used by NP, random, is not reproducible across different machines or sessions. Sample use case. Running the same code with random state none on two different machines might yield different results. Fixes. Specify a specific integer value for random state to ensure reproducibility. Use a dedicated random state instance initialized with a fixed seed for all random number generation tasks. sklearn, utils, validation, check is fitted. Description. This function is a utility in scikit-learn that checks if a given estimator has been fitted. It raises an exception if the estimator has not been fitted, ensuring that you don't attempt to use an unfitted model for prediction or other operations. Inputs. Estimator. The estimator object to be checked. This can be any scikit-learn estimator like a classifier, regressor, or transformer. Attributes. This is a list of strings. each representing an attribute that should be present in the fitted estimator. These attributes are typically used to store information about the model learned during the fitting process. For example, a linear regression model would have attributes like core or intercept that store the fitted coefficients and intercept. By default, fit attributes is set to n features in n sample scene. Feature names n. Alarani. This parameter determines whether all or any of the specified attributes need to be present in the estimator. The default is all, meaning that the estimator must have all the attributes from the attributes list if set to any. At least one of the attributes must be present. Outputs. No explicit output. The function either raises an exception if the estimator is not fitted or silently returns if the estimator is fitted. Steps. Checks if the estimator is an instance of base estimator or a subclass. For each attribute specified in the attributes list. Checks if the attribute exists on the estimator. If all attributes are present, if Alarani is all or at least one attribute is present, if Alarani is any, the function returns without doing anything. If any of the specified attributes are missing, the function raises a not fitted error exception. Metrics. No specific metrics are associated with this function as it is purely a validation check. Visualization plots. This function is not involved in visualization, so no plots are produced. Fine-tune parameters. Attributes. You can adjust this list to include any specific attributes that you need to check for your estimator. Alarani. If you want to check for the presence of at least one attribute from the list, you can set this parameter to any. Uncertainty methods. This function does not relate to uncertainty methods or model predictions. Challenges and fixes. Challenge 1. The function can be overly strict and might raise an exception if the fitted estimator has attributes that are not explicitly listed in the attributes list. Sample use case. You have a custom estimator that has a fitted attribute called model weights. But you are not checking for this attribute in the attributes list. Fixes to overcome this include all necessary attributes in the attributes list. Challenge 2. If Alarani is set to all but the estimator has only a subset of the attributes specified, a not fitted error will be raised. This could be a false positive if a specific attribute is not needed for the particular use case. Sample use case. You are using a pre-trained model that only has attributes like n features in n. Feature names n. But you are checking for n sample scene. Fixes. You can either adjust the attributes list to remove the unnecessary attribute or set Alarani to any to check for at least one attribute. sklearn, utils, validation, check memory. Description. The check memory function is a utility function in scikit-learn used to optimize the performance of computationally expensive functions by caching their results. It essentially creates a memory-based cache that stores the results of function calls, allowing subsequent calls with the same arguments to retrieve the cached result instead of re-executing the function. This is particularly helpful in scenarios where the function is called multiple times with the same inputs, saving significant time and computational resources. Inputs. Cachedia. The directory to use for caching. If none, the default cachedia will be used. See joblib. Memory. Cachedia. Verbose level of verbosity. Outputs. Memo is a decorator that caches the return value of the decorated function based on its arguments. This decorator is used to transform any function into a memoized version. Clear. A function to clear the cache. This allows you to manually remove cached results from the memory. Steps. Create a joblib memory object with the specified cachedia and verbose settings. Use the memory object's cache method to decorate the provided function. This method creates a memoized version of the function that stores its results in the cache. The memoized function will automatically check the cache for results before executing the actual function. If a cached result exists for the given arguments, it will be retrieved and returned. Otherwise, the function is executed. Its result is stored in the cache and then returned. Metrics. Cache hit ratio percentage of function calls that retrieve results from the cache. Cache size, the amount of memory used by the cache. Visualization plots. Cache hit ratio over time, a line plot showing the percentage of cache hits over time. Cache size over time, a line plot showing the amount of memory used by the cache over time. Fine-tune parameters. Cachedia specifies the directory to store the cache files. Verbose controls the level of logging information. Uncertainty methods. Not applicable. This function is deterministic, and its output is solely determined by its input arguments and the cached results. Challenges and fixes. Challenge 1: insufficient disk space. Sample use case that resulted in challenge 1: when the cache size grows too large, it might exceed the available disk space, causing errors or performance issues. Fixes to challenge 1. Increase the disk space allocated for the cache. Set a maximum cache size to limit the amount of data stored in the cache. Challenge 2: cache corruption. Sample use case that resulted in challenge 2: if the cache files are corrupted or become inconsistent, it might lead to incorrect results or errors. Fixes to challenge 2. Clear the cache and regenerate the cached results. Use a more robust cache storage mechanism, such as a database. Challenge 3: cache invalidation. Sample use case that resulted in challenge 3: if the function's logic changes, the existing cached results might become invalid, leading to incorrect outputs. Fixes to challenge 3. Clear the cache whenever the function's logic is updated. Implement a versioning scheme for the cached results to ensure that outdated results are not used. Challenge 4: cache contention. Sample use case that resulted in challenge 4: if multiple processes or threads access the cache concurrently, it can lead to contention and performance degradation. Fixes to challenge 4. Use a thread-safe cache implementation. Use a distributed cache that can be accessed from multiple nodes. YAML. sklearn, utils, validation, check symmetric. Description. This function checks if a given array is symmetric, meaning that it is equal to its transpose. Inputs. Array A to D array that needs to be checked for symmetry. Toll a float specifying the tolerance for comparing elements. Default is 1E08. Raise warning, a Boolean value indicating whether to raise a warning if the array is not symmetric. Default is true. Outputs. None, the function returns none. Warning, if raise warning is set to true and the array is not symmetric, a user warning is raised. Steps. The function checks if the given array is a 2D array using isInstance array. NP, ND array and array. NDIM2. If the array is a 2D array, it calculates the transpose of the array using array T. It then compares the original array with its transpose using NP, all close array. Array T at all. If the arrays are not close within the specified tolerance, a warning is raised if raise warning is true. Metrics. Tolerance. This parameter controls the level of accuracy used to compare the array with its transpose. A higher tolerance value means that the comparison will be less strict. Visualization plots. Heat map of the original array. Heat map of the transposed array. Fine-tune parameters. Tool. This parameter controls the tolerance used to compare the array with its transpose. Raise warning. This parameter controls whether a warning is raised if the array is not symmetric. Uncertainty methods. This function doesn't provide any uncertainty methods. Challenges and fixes. Challenge 1. The array may not be perfectly symmetric due to floating point errors. Sample use case that resulted in challenge 1 when dealing with arrays generated through numerical calculations. Small numerical errors can lead to discrepancies between the original array and its transpose. Fixes to challenge 1. Increase the tolerance value tool to accommodate for potential rounding errors. Challenge 2. The array might not be symmetric due to errors in data entry or manipulation. Sample use case that resulted in challenge 2. Incorrect data input or transformations can lead to an array that is not truly symmetric. Fixes to challenge 2. Carefully review the data entry process and data manipulation steps to identify and correct any inconsistencies or errors. sklearn, utils, validation, columnar 1D. Description. The columnar 1D function is a utility within Scikit-learn's validation module that ensures an input is either a one-dimensional array or a single column from a two-dimensional array. This function is frequently used in machine learning tasks, particularly when dealing with data features that should be represented as single vectors. Inputs. X. This is the input data. It can be either a one-dimensional array or a two-dimensional array matrix where each row represents a sample, and each column represents a feature. Outputs. X1D. This is the output. It is guaranteed to be a one-dimensional array, regardless of the input shape of X. If X was already one-dimensional, it is returned as is. If X was two-dimensional, a single column is extracted and returned as a one-dimensional array. Steps. Shape check. The function first checks the shape of the input data X. One-dimensional input. If X is already one-dimensional, has a single dimension, it is directly returned as the output. Two-dimensional input. If X is two-dimensional, the function checks if it has only one column. If so, it is reshaped into a one-dimensional array and returned. Invalid input. If X is not one-dimensional or does not have a single column when two-dimensional, an error is raised, indicating that the input does not satisfy the required format. Challenges and fixes. Challenge 1. Incorrect input shape. Sample use case that resulted in challenge 1 providing an input X that has more than one column, when it should be one-dimensional or a single column. Fixes to challenge 1. Ensure that the input data is either a one-dimensional array or a two-dimensional array with a single column. You can use NumPy's reshape function to adjust the shape if necessary. Challenge 2. Unexpected array type. Sample use case that resulted in challenge 2 providing input X in a format that is not compatible with NumPy arrays, such as a list or a pandas series. Fixes to challenge 2. Convert the input data to a NumPy array using NP array before passing it to columnar 1D. sklearn, utils, validation, hasFit parameter. Description. The hasFit parameter function is used to check if an estimator has a specific parameter in its fit method. This function is particularly useful for ensuring the compatibility of estimators with certain pipelines or workflows that require specific parameters. Inputs. Estimator. This is an instance of an estimator object, e.g., a model from Scikit-learn. Parameter. This is the name of the parameter you want to check for in the fit method. Boolean. The function returns true if the specified parameter exists in the fit method of the estimator, and false otherwise. The function first inspects the signature of the fit method of the estimator using introspection tools. It then checks if the provided parameter is present as a named argument in the fit method. Signature metrics. This function doesn't directly involve metrics, it serves a purely structural and validation purpose. Visualization plots. This function doesn't generate any visualizations. This function doesn't have fine-tuning parameters. This function doesn't involve uncertainty estimation methods. Challenge 1. The estimator may not have a clearly defined fit method. For example, custom estimators might implement fit in a less standard way. Sample use case: creating a custom estimator that doesn't strictly follow scikit-learn conventions. For defining the fit method. Fixes to challenge 1. Ensure that your custom estimator defines a fit method that adheres to scikit-learn's expected structure. Consider using a more general approach for inspecting the estimator, such as using inspect, signature, or a similar method. Challenge 2. The fit method might have the parameter, but it may be optional using a default value. Sample use case: a fit method accepts a parameter named sample weight, but it defaults to none if not provided. Fixes to challenge 2. Use the hasFit parameter function in combination with other checks to determine if the parameter is truly required by your workflow. If the parameter is optional, consider providing a default value to ensure consistent behavior. Scikit-learn utils meta-estimators. Description meta-estimators in Scikit-learn. Scikit-learn are a powerful concept that allows you to build complex machine learning pipelines by combining different estimators into a single unified structure. They provide a convenient way to encapsulate and reuse common machine learning patterns, simplifying the development and deployment of sophisticated models. Inputs. Estimators: one or more base estimators, which are the core building blocks of the meta-estimator. These estimators can be classifiers, regressors, transformers, or other compatible scikit-learn models. Parameters: configuration settings for the meta-estimator, including hyperparameters for the underlying estimators and control parameters for the meta-estimator's behavior. Outputs. Predictions: output of the meta-estimator, typically in the form of class labels, regression values, or transformed data, depending on the specific meta-estimator and the task at hand. Fitted model: a trained meta-estimator, containing the learned parameters of the underlying estimators and the meta-estimator itself. Steps. Initialization: the meta-estimator is created with specified base estimators and hyperparameters. Training: the meta-estimator is fit to the training data, which typically involves training the underlying estimators and potentially learning additional parameters. Prediction: the trained meta-estimator is used to make predictions on new data, utilizing the trained underlying estimators and its own logic. Metrics. Performance metrics: evaluation metrics relevant to the task classification accuracy, regression error, etc., are calculated to assess the effectiveness of the meta-estimator. Model complexity metrics like the number of parameters or model size can be used to understand the complexity of the meta-estimator. Visualization plots. Decision boundary plots visualize the decision boundaries learned by classification models. Feature importance plots show the relative importance of features in the model. Residual plots for regression models visualize the difference between predicted and actual values to identify patterns or outliers. Fine-tune parameters. Hyperparameter optimization. Search for optimal values for hyperparameters using techniques like grid search or random search. Feature engineering. Experiment with different feature transformations to improve model performance. Uncertainty methods. Confidence intervals. Calculate confidence intervals for predictions to estimate the uncertainty associated with them. Bayesian inference. Use Bayesian methods to model the uncertainty in model parameters. Challenges and fixes. Challenge 1. Overfitting. Meta estimators can overfit if the underlying estimators are too complex, or if the hyperparameters are not carefully tuned. Sample use case that resulted in challenge 1 using a high-capacity neural network as an underlying estimator without proper regularization. Fixes to challenge 1. Regularization. Apply regularization techniques L1, L2. Drop out to the underlying estimators to prevent overfitting. Early stopping. Stop training when the model's performance on a validation set starts to decline. Challenge 2. Poor generalization. Meta estimators can have poor generalization performance if their training data is not representative of the real-world data. Sample use case that resulted in challenge 2. Training a model on a small dataset with limited diversity. Fixes to challenge 2. Data augmentation. Generate synthetic data to increase the size and diversity of the training set. Data preprocessing. Apply appropriate data preprocessing techniques to ensure that the data is consistent and suitable for training. Challenge 3. Computational complexity. Some meta estimators can be computationally expensive to train and predict. Sample use case that resulted in challenge 3 using a meta estimator with a large number of underlying estimators or complex operations. Fixes to challenge 3. Efficient algorithms. Utilize optimized algorithms or libraries for training and prediction. Distributed computing. Distribute the computation across multiple machines for parallel processing. Challenge 4. Interpretability. Meta estimators can be difficult to interpret, especially if they involve multiple layers of estimators. Sample use case that resulted in challenge 4 using a deep learning meta estimator with a complex architecture. Fixes to challenge 4. Feature importance analysis. Analyze the importance of features to understand the model's decision-making process. Visualization techniques. Utilize visualization tools to visualize the model's behavior and decision boundaries. sklearn, utils, meta-estimators, available IF. Description. The available IF meta-estimator decorator provides a mechanism to dynamically enable or disable a scikit-learn estimator based on the presence of specific attributes in the input data. This decorator checks if a particular attribute is present in the data before initiating the estimator, preventing the estimator from being used when its required attributes are missing. It enhances code robustness by gracefully handling scenarios where an estimator might not be suitable for the given dataset. Inputs. Estimator. The scikit-learn estimator to be conditionally enabled or disabled based on the presence of specific attributes in the input data. Attribute names. A list of attribute names that must be present in the input data for the estimator to be active. The decorator checks if these attributes are available in the data before initializing the estimator. Outputs. Decorated estimator. The original estimator decorated with the available IF functionality. This decorated estimator will only be instantiated and used if the required attributes are present in the input data. Steps. Attribute check before initializing the estimator. The available if decorator checks if all the attributes specified in attribute names are present in the input data. Conditional instantiation if all required attributes are found. The decorated estimator is instantiated and ready for use. Otherwise, the estimator is not instantiated, and an informative error message is raised. Metrics. Not directly applicable. This meta estimator decorator focuses on ensuring the availability of necessary attributes and does not directly evaluate the performance of the underlying estimator. Visualization plots. Not directly applicable. The available if decorator is primarily a structural element to conditionally enable estimators and does not involve visualization. Fine-tune parameters. Not directly applicable. The available if decorator does not introduce any fine-tuning parameters. It primarily functions as a conditional enablement mechanism. Uncertainty methods. Not directly applicable. The available if decorator does not deal with uncertainty estimations or methods. Challenges and fixes. Challenge 1. The absence of required attributes might lead to unexpected errors during model training or prediction if the available if decorator is not employed. Sample use case. A machine learning model requiring categorical features might encounter issues if the input data lacks categorical columns. Fixes. Implementing the available if decorator ensures that the model is only instantiated when all required attributes are present, preventing unexpected errors. Challenge 2. If an estimator's functionality relies on specific attributes, its use without the available if decorator might result in erroneous outputs or model failures. Sample use case. A time series forecasting model might necessitate timestamps in the input data. Without the available if decorator, using the model on data lacking timestamps could produce inaccurate predictions. Fixes. Using the available if decorator ensures that the model is only active when the required timestamps are present, ensuring the integrity of its predictions. sklearn, utils, class weight. Description. The class weight function in scikit-learn sklearn is used to calculate weights for each class in a classification problem. These weights are used to balance the dataset when there is a significant class imbalance. Class imbalance occurs when one or more classes have significantly fewer instances compared to others. This imbalance can lead to biased model training, where the model favors the majority class and performs poorly on the minority class. Inputs. YA1D array containing the target labels for the training data. Class weight. A string or dictionary specifying the class weights. Outputs. Class weights. A dictionary mapping each class to its corresponding weight. Steps. If the class weight parameter is set to balanced, the function calculates class weights inversely proportional to the number of samples in each class. If a dictionary is provided, the function uses the weights specified in the dictionary. If the class weight parameter is not specified or set to none, all classes are assigned equal weights. Metrics. Precision. The ratio of correctly predicted positive instances to the total number of predicted positive instances. Recall. The ratio of correctly predicted positive instances to the total number of actual positive instances. F1 score. The harmonic mean of precision and recall. Visualization plots. Confusion matrix. A visual representation of the model's performance, showing the number of correctly and incorrectly classified instances for each class. Precision recall curve. A plot showing the trade-off between precision and recall for different classification thresholds. Receiver operating characteristic ROC curve. A plot showing the true positive rate sensitivity Against the false positive rate 1 specificity for different classification thresholds. Fine-tune parameters. Class weight. This parameter can be used to specify the class weights manually or to use the balanced option to automatically calculate weights. Uncertainty methods. Confidence intervals. Estimating confidence intervals for the predicted probabilities can provide a measure of uncertainty. Bayesian methods. Using Bayesian methods to model the data and incorporate prior information can capture uncertainty in the model parameters. Challenges and fixes. Challenge 1. Class imbalance can lead to biased model training, resulting in poor performance on the minority class. Sample use case that resulted in challenge 1. If fraud detection dataset where only a small percentage of transactions are fraudulent. Fixes to challenge 1. Use the class weight parameter with the balanced option or specify custom weights to balance the dataset. Challenge 2. Determining the optimal class weights can be challenging, as it depends on the specific dataset and the desired trade-off between precision and recall. Sample use case that resulted in challenge 2. A medical diagnosis dataset where different classes have different costs associated with misclassification. Fixes to challenge 2. Experiment with different class weights and evaluate the model performance using appropriate metrics, such as F1 score, to find the best balance. sklearn, utils, class weight, compute class weight. Description. The compute class weight function in scikit-learn sklearn calculates class weights based on the distribution of classes in the input data. This is particularly useful for addressing class imbalance in classification tasks, where some classes have significantly fewer samples than others. Inputs. Class weight. This parameter specifies the type of class weight computation to be used. It can take one of the following values. Balanced. This assigns weights inversely proportional to class frequencies in the input data. It's commonly used to counter class imbalance. Balanced subsample. Similar to balanced, but weights are adjusted by the proportion of the smallest class in the training set. A dictionary with keys as class labels and values as corresponding weights. This allows for manual specification of class weights. Why this input is a 1D array containing the target class labels for the training data. Outputs. Class weights. A 1D array containing the computed class weights. The length of this array is equal to the number of unique classes in the input data. Each element corresponds to the weight assigned to the respective class. Steps. 1. Class frequency analysis. The function first determines the frequency number of instances of each class in the input target labels y. 2. Weight calculation. Depending on the specified class weight value, it applies the appropriate weighing scheme. Balanced weight. Number of samples in class, number of unique classes. Balanced subsample weight. Number of samples in smallest class, number of samples in class. Number of unique classes. 3. Weight assignment. The calculated weights are assigned to each class, representing the relative importance of that class in the learning process. Metrics. Accuracy. The accuracy of the model, which is a measure of how many predictions are correct. Precision. The precision of the model, which is a measure of how many of the positive predictions are actually correct. Recall. The recall of the model, which is a measure of how many of the actual positive cases are correctly predicted. F1 score. The F1 score of the model, which is a harmonic mean of precision and recall. Visualization plots. Confusion matrix. A confusion matrix can be used to visualize the performance of the model, showing the number of true positives, true negatives, false positives, and false negatives. Receiver operating characteristic ROC curve and ROC curve plots the true positive rate against the false positive rate for different classification thresholds. Precision recall curve. A precision recall curve plots precision against recall for different classification thresholds. Fine-tune parameters. Class weight. This parameter allows you to specify the desired weighing scheme for class imbalance. Fine-tuning this parameter by experimenting with different options can improve model performance. Uncertainty methods. Confidence intervals. By calculating confidence intervals for model predictions, you can quantify the uncertainty associated with those predictions. Bayesian methods. Bayesian methods can be used to incorporate prior knowledge about the distribution of classes and provide a more nuanced estimate of uncertainty. Challenges and fixes. Challenge 1. Overfitting. If the class weights are not carefully chosen, the model might overfit to the majority class, leading to poor performance on minority classes. Sample use case that resulted in challenge 1. Training a classifier on a dataset with a large class imbalance. The classifier learns to predict the majority class accurately, but performs poorly on the minority class. Fixes to challenge 1. Use the balanced or balanced subsample weighing schemes to give more weight to the minority class. Use techniques like oversampling, undersampling, or synthetic minority oversampling techniques mode to balance the data before training the model. Challenge 2. Unrealistic weights. In some cases, assigning weights based on class frequencies might not be the optimal approach, especially if the data is noisy or if there are underlying relationships between classes. Sample use case that resulted in challenge 2. Training a classifier on a dataset where the majority class contains a high number of mislabeled instances. Fixes to challenge 2. Carefully analyze the data and consider domain expertise to determine the appropriate weighing scheme. Experiment with different weighing schemes to find the one that works best for the specific dataset. Use techniques like data cleaning and outlier detection to improve the quality of the data before applying class weighing. sklearn, utils, class weight, computes sample weight. Description. This function calculates sample weights for imbalanced datasets. It helps to address class imbalance by assigning higher weights to samples from underrepresented classes, effectively giving them more influence during model training. Inputs. Class weight. A dictionary with keys representing class labels and values representing their weights. If balanced, it automatically calculates weights inversely proportional to the class frequencies. Y. The target variable is a 1D array or list, representing the true class labels of the samples. Outputs. Sample weight. A 1D array of weights assigned to each sample, reflecting the class imbalance. Steps. Calculate class frequencies. The function first determines the frequency of each class in a provided target variable y. Calculate weights. If class weight is balanced, the weights for each class are inversely proportional to their frequencies. Otherwise, the weights specified in the class weight dictionary are used. Assign weights to samples. The calculated weights are then assigned to each sample based on its corresponding class label. Metrics. F1 score. This metric measures the balance between precision and recall, often used in imbalanced datasets. AUC area under the curve. A metric for evaluating the performance of binary classifiers. Useful for imbalanced data as it considers the ranking of samples. Visualization plots. Class distribution plot shows the distribution of samples across different classes, highlighting the imbalance. Precision recall curve plots precision against recall at various thresholds, providing insights into the model's performance on different class balances. Fine-tune parameters. Class weight. This parameter determines how sample weights are calculated. Experiment with different values, e.g., balanced. Custom dictionary to optimize for the specific dataset. Uncertainty methods. Confidence intervals. Calculate confidence intervals around the model's predictions to assess the uncertainty associated with each prediction, especially for minority classes. Bootstrap resampling. Repeatedly sample data with replacement to estimate the variability of the model's performance and identify influential samples. Challenges and fixes. Challenge 1. Overfitting to the majority class. If weights are not adjusted correctly, the model may overfit to the majority class, resulting in poor performance on minority classes. Sample use case. In a medical diagnosis dataset with a high prevalence of healthy patients, the model might learn to predict healthy outcomes accurately but fail to identify rare diseases. Fixes. Use balanced class weight. This automatically assigns higher weights to minority classes, reducing overfitting. Fine-tune the class weights. Experiment with custom weight values in the class weight dictionary to find the optimal balance. Challenge 2. Difficulty in evaluating model performance. Standard metrics like accuracy can be misleading in imbalanced datasets. Sample use case. A model with high accuracy but low recall for the minority class might not be useful in applications where detecting minority instances is crucial. Fixes. Use appropriate metrics. Focus on metrics like F1 score, AUC, or precision recall curves to assess the model's performance on minority classes. Use stratified cross-validation. Ensure that the distribution of classes is maintained in each fold of cross-validation to obtain a more accurate evaluation. sklearn, utils, multiclass. Description. This module provides utility functions for handling multi-class classification problems in Scikit-learn. These functions simplify the process of converting between different representation formats of multi-class labels, such as one-hot encoding, ordinal encoding, and label-based encoding. Inputs. Why? This is the target variable representing class labels for the data. It can be in various forms, including integer labels, string labels, or one-hot encoded vectors. Outputs. The output format depends on the specific function used. For example, ordinal labels to indices. This function returns a list of indices corresponding to the ordinal labels provided. Class distribution. This function returns the distribution of classes in the input target variable. Steps. The functions in this module perform transformations on the input target variable y. Metrics. Accuracy. This metric measures the proportion of correctly classified samples. Precision. This metric measures the proportion of true positive predictions out of all positive predictions. Recall. This metric measures the proportion of true positive predictions out of all actual positive samples. F1 score. This metric combines precision and recall into a single score. Visualization plots. Confusion matrix. This plot visualizes the performance of a classifier by showing the number of true and false predictions for each class. ROC curve. This plot shows the trade-off between true positive rate and false positive rate for different classification thresholds. Fine-tune parameters. None. The functions in this module are generally used for data preparation and do not have tunable parameters. Uncertainty methods. None. The functions in this module are not designed for uncertainty estimation. Challenges and fixes. Challenge 1: handling imbalanced datasets. Sample use case when the classes in the target variable are not equally represented. Certain classifiers might be biased towards the majority class. Fixes. Resampling techniques: oversampling the minority class or undersampling the majority class can help balance the dataset. Class weights: assigning higher weights to samples from the minority class during training can address the imbalance. Challenge 2: handling large number of classes. Sample use case: classifying data with a very large number of classes can lead to computational challenges and memory issues. Fixes. Feature selection: selecting relevant features can reduce the dimensionality of the data and improve efficiency. Ensemble methods: combining multiple classifiers can improve the performance and robustness of PE model. Hierarchical classification: breaking down the classification task into smaller sub-problems can simplify the process. sklearn, utils, multi-class, type of target. Description. This function determines the type of target that is being used in a machine learning model. This is useful for understanding the type of data being used, as well as for selecting the appropriate machine learning model. Inputs. Why this is the target variable, which can be a 1D array, a 2D array, or a list. Outputs. Target type: this is a string that describes the type of target. Possible values are binary: the target is binary, e.g. 0 or 1, true or false. Multiclass: the target is multiclass, e.g. 0, 1, 2, or A, B, C. Multilabel indicator: the target is a multilabel indicator, which is a 2D array where each row represents a sample and each column represents a label. Continuous: the target is continuous, e.g. a number. Unknown: the target type could not be determined. Steps. The function first checks if the target is a 1D array. If so, it checks the number of unique values in the target. If there are only 2 unique values, it returns binary. If there are more than 2 unique values, it returns multiclass. If the target is a 2D array, it checks if all of the values are either 0 or 1. If so, it returns multilabel indicator. If the target is a list, it checks the type of the first element in the list. If the first element is an integer or a float, it returns continuous. If none of the above conditions are met, the function returns unknown. Metrics: none. Visualization plots: none. Fine-tune parameters: none. Uncertainty methods: none. Challenges and fixes. Challenge 1: the target variable might contain a mix of string and numeric values. Sample use case that resulted in challenge 1: the target variable could contain a mix of strings and numeric values, like 0, 1, A, B. This could lead to an incorrect determination of the target type. Fixes to challenge 1: the function should be able to handle cases where the target variable contains a mix of string and numeric values. This could be done by converting all values to strings and then checking the number of unique values. Challenge 2: the target variable might contain missing values. Sample use case that resulted in challenge 2: the target variable could contain missing values, such as none. This could lead to an incorrect determination of the target type. Fixes to challenge 2: the function should be able to handle cases where the target variable contains missing values. This could be done by first imputing the missing values before determining the target type. sklearn utils multiclass is multilabel. Description: the is multilabel function from Scikit learns multiclass module is a utility function used to determine if a dataset is multilabel. In multilabel classification, each sample can be assigned to multiple labels simultaneously. This function helps in identifying if the dataset structure aligns with this type of classification. Inputs. Why this is the input array or data structure containing the target labels. It can be a NumPy array, pandas data frame, or any other structure that can be interpreted as a collection of labels. Outputs. Bool. The output is a Boolean value. It returns true if the dataset is multilabel, indicating that each sample can have multiple labels. Otherwise, it returns false, signifying that each sample can have only one label. Steps. Analyze data structure. The function examines the input data structure, Y, to determine if it represents a multilabel dataset. It looks for characteristics like the presence of multiple labels per sample or data structures that allow for multiple labels per data point. Metrics. None. This function doesn't involve any specific metrics for evaluation, as it simply checks for a specific characteristic in the dataset. Visualization plots. None. This function doesn't involve any visualizations. Fine-tune parameters. None. This function doesn't have any parameters to fine-tune. Uncertainty methods. None. This function is for data structure analysis and does not deal with uncertainty. Challenges and fixes. Challenge 1. Data structure compatibility. The function might encounter challenges when dealing with data structures that are not readily interpreted as representing multilabel datasets. Sample use case that resulted in challenge 1. A dataset where labels are stored as a single string, like label 1, label 2, might not be recognized as multilabel by the function. Fixes to challenge 1. Pre-processing the data to explicitly convert the labels into a format that the function can interpret as multilabel. This could involve splitting the string into a list or using a data structure that represents multiple labels per sample. Challenge 2. Data type mismatch. If the input data structure contains elements of different data types, the function might not be able to correctly identify if the dataset is multilabel. Sample use case that resulted in challenge 2. A dataset with labels stored as strings and numeric values might lead to confusion for the function. Fixes to challenge 2. Ensure that the data type of the input labels is consistent. If the labels are stored as a mixture of data types, convert them to a single type, such as strings or numbers. sklearn, utils, multiclass, unique labels. Description. The unique labels function from Scikit learns utils. Multiclass module is a utility for extracting unique labels from a collection of input data. It is commonly used in multi-class classification problems to identify the distinct classes present in the data. Inputs. Y1. This input represents the first set of labels, which can be an array-like structure containing integer or string labels. Y2. This is an optional second set of labels. It follows the same format as Y1. If provided, the function will extract unique labels from both input sets. Outputs. Unique labels. This output is a NumPy array containing the unique labels extracted from the input data. The labels are sorted in ascending order. Steps. Label extraction. The function first gathers all labels from the input arrays Y1 and Y2 if provided. Duplicates removal. It then uses the np unique function to identify and remove any duplicate labels, ensuring that only unique labels remain. Sorting. The unique labels are then sorted in ascending order using the np sort function. This ensures a consistent and predictable order for the output labels. Metrics. Label count. The number of unique labels in the output array. This metric can be useful for understanding the complexity of the classification problem. Label diversity, the distribution of labels within the unique labels set. This can provide insights into the balance of the classes in the data. Visualization plots. Label distribution histogram, a histogram depicting the frequency of each unique label. This plot helps visualize the class distribution and potential class imbalances. Fine-tune parameters. None, the function does not have any adjustable parameters. Uncertainty methods. None, this function does not involve uncertainty estimations. Challenges and fixes. Challenge 1, incorrect input format. Sample use case that resulted in challenge 1, providing labels in a format that is not supported by the function, such as lists containing mixed data types. Fixes to challenge 1 ensure that the input labels are provided in a supported format, such as a NumPy array of integers or strings. Challenge 2, handling missing labels. Sample use case that resulted in challenge 2, input data contains missing labels or labels that are not properly defined. Fixes to challenge 2, pre-process the data to handle missing labels by assigning them a specific value or removing them from the dataset. sklearn, utils, xstmath. Description: the sklearn, utils, xstmath module provides optimized numerical routines for common operations in machine learning, particularly for working with matrices and vectors. These routines often leverage efficient implementations in libraries like BLAS and LAPACK. Inputs. Input matrices or vectors. These are typically NumPy arrays that represent data. Features or model parameters. Optional parameters. These can include parameters like thresholds, regularization strengths, or other settings specific to the function. Outputs. Computed results. The outputs depend on the specific function but typically involve transformed matrices, vectors, or other calculated values. Steps. Matrix vector transformations. Functions may perform operations like matrix multiplication, singular value decomposition (SVD), or eigenvalue decomposition. Optimization. Some functions leverage techniques like QR factorization or Kolsky decomposition for efficient computation. Regularization. Functions like safesparse and logsumMakesUp can incorporate regularization to handle sparse data or prevent numerical issues. Metrics. Runtime performance. The speed of computations is often measured, particularly when comparing different implementations or algorithms. Accuracy for operations like SVD. The accuracy of the results can be evaluated against known values or theoretical expectations. Numerical stability measures are taken to ensure that calculations are numerically stable and avoid issues like overflow or underflow. Visualization plots. Matrix visualizations. Visualizations like heat maps or dendrograms can be used to analyze the structure of matrices, especially for dimensionality reduction or clustering tasks. Scatter plots. Plots can show the relationships between transformed data points to understand the effects of operations like PCA or MDS. Fine-tune parameters. Regularization strength. This parameter can be adjusted to control the amount of regularization applied, affecting stability and generalization. Thresholds. Some functions use thresholds to filter values or determine convergence criteria, which can be fine-tuned to optimize performance. Numerical precision. The precision of calculations can be adjusted for specific applications, trading off speed for accuracy. Uncertainty methods. Bootstrap resampling. For methods like SVD, uncertainty can be estimated by repeatedly sampling the data and computing the decomposition multiple times. Confidence intervals based on resampling or other statistical techniques. Confidence intervals can be calculated to quantify the uncertainty in the results. Challenges and fixes. Challenge 1: handling sparse data. Sample use case: working with datasets containing many zeros can lead to inefficient computations if not handled properly. Fixes: the module provides functions like safesparse that efficiently handle sparse matrices, preventing unnecessary operations on zero values. Challenge 2: numerical stability. Sample use case calculations involving very large or very small numbers can lead to overflow or underflow errors. Fixes: functions like logsumMakesUp use logarithmic transformations to improve numerical stability, particularly when dealing with sums of exponentials. Challenge 3: memory efficiency. Sample use case: working with large matrices can lead to excessive memory usage, especially when performing operations like matrix multiplication. Fixes: some functions, like sparse are optimized to work with sparse matrices, reducing memory requirements. sklearn, utils, extmart, safesparse. Description: this function performs a safe dot product between two arrays, ensuring that the result is always a dense array. It handles sparse matrices efficiently by utilizing optimized sparse matrix operations, improving computational efficiency compared to using standard NumPy dot products. Inputs. The first input array. It can be a dense array NumPy ND array or a sparse matrix CP, sparse. B. The second input array. It can also be a dense array or a sparse matrix. Outputs. The result of the dot product. It is always a dense NumPy array, regardless of the input array types. Steps. If both input arrays are dense, it performs a standard NumPy dot product NP. Dota. B. If at least one input array is sparse, it utilizes the optimized sparse matrix operations from the CP, sparse library. Metrics. Computational efficiency. This function aims to optimize the dot product operation, especially when handling sparse matrices, by leveraging sparse matrix operations for faster calculations. Visualization plots. No specific visualization plots are associated with this function. Fine-tune parameters. None. Uncertainty methods. This function does not involve any uncertainty estimation or prediction. Challenges and fixes. Challenge 1. Sample use case that resulted in challenge 1: attempting to perform a dot product with a sparse matrix that has a large number of non-zero elements may lead to memory issues if the result is not handled efficiently. Fixes to challenge 1: this function utilizes optimized sparse matrix operations from CP, sparse, which helps to minimize memory usage and computational overhead when handling large sparse matrices. Challenge 2. Sample use case that resulted in challenge 2: performing dot products between very large arrays can lead to significant time and memory consumption, particularly in cases involving dense matrices. Fixes to challenge 2: this function leverages efficient sparse matrix operations if either input array is sparse, which can significantly reduce time and memory requirements compared to using standard NumPy dot products for dense matrices. sklearn, utils, extmart, randomized range finder. Description: the randomized range finder function efficiently determines a suitable range for a given array by using random sampling. It helps in identifying the minimum and maximum values needed for effective scaling or normalization of the data. This is particularly useful when dealing with large datasets, where calculating the exact minimum and maximum values can be computationally expensive. Inputs. X a NumPy array representing the data for which the range is to be determined. Outputs. Minmax a tuple containing the minimum and maximum values found within the randomly sampled subset of the input array X. Steps. Randomly samples a subset of data points from the input array X. Calculates the minimum and maximum values within the sampled subset. Returns the minimum and maximum values as a tuple. Metrics. Accuracy. The accuracy of the range estimation is directly related to the size of the randomly sampled subset. A larger subset generally provides a more accurate estimation. Efficiency. The randomized range finder function is designed to be efficient, especially when dealing with large datasets. It avoids the need to scan the entire dataset for the minimum and maximum values, making it computationally faster. Visualization plots. Histogram. A histogram of the data can be used to visualize the distribution of values and provide insights into the potential range. Fine-tune parameters. N samples. The number of samples to be randomly selected from the input array X. Increasing this value generally improves the accuracy of the range estimation but can also increase computational time. Uncertainty methods. Confidence intervals. Confidence intervals can be used to quantify the uncertainty in a estimated range. Challenges and fixes. Challenge 1. The estimated range might not be accurate if the randomly sampled subset is not representative of the entire dataset. Sample use case that resulted in challenge 1. If the dataset has outliers, a small sample might not include them, leading to an inaccurate range estimation. Fixes to challenge 1. Increase the size of the randomly sampled subset to ensure better representation of the data. Challenge 2. The function can be sensitive to the presence of extreme outliers. Sample use case that resulted in challenge 2. If the data has extreme outliers, the estimated range might be significantly affected by these outliers. Fixes to challenge 2. Consider applying robust estimators for the minimum and maximum values, which are less sensitive to outliers. Alternatively, use a technique like winsorization to clip the outliers before applying the rangefinder. sklearn, utils, xsmart, randomized SVD. Description: a randomized algorithm for computing the singular value decomposition SVD of a matrix. This algorithm is faster than the standard SVD algorithm for large matrices, especially when only a few singular values and vectors are needed. Inputs: X, the input matrix for which the SVD is to be computed. N components, the number of singular values and vectors to compute. If none, all singular values and vectors are computed. November samples, the number of extra singular values and vectors to compute to improve the accuracy of the algorithm. Niter, the number of iterations to perform in the randomized SVD algorithm. Outputs: U, the left singular vectors of the matrix X. S, the singular values of the matrix X. V, the right singular vectors of the matrix X. Steps: generate a random matrix with dimensions n components. November samples. X. Shape 1. Multiply the random matrix by the input matrix X. Compute the QR decomposition of the product. Compute the SVD of the R matrix from the QR decomposition. Select the top n components singular values and vectors from the SVD of R. Project the original input matrix X onto the selected singular vectors to obtain the left singular vectors U. Metrics: accuracy. The accuracy of the computed SVD can be measured by comparing the computed singular values and vectors to the results of the standard SVD algorithm. Visualization plots: Singular value spectrum. A plot of the singular values in descending order can be used to visualize the distribution of the singular values. Scatter plot of the left and right singular vectors. A scatter plot of the left and right singular vectors can be used to visualize the relationship between the singular vectors. Fine-tune parameters. N components. This parameter controls the number of singular values and vectors to compute. Increasing this parameter will improve the accuracy of the algorithm, but it will also increase the computation time. November samples. This parameter controls the number of extra singular values and vectors to compute. Increasing this parameter will improve the accuracy of the algorithm, but it will also increase the computation time. Uncertainty methods. Bootstrap. The bootstrap method can be used to estimate the uncertainty in the computed singular values and vectors. Challenges and fixes. Challenge 1. The randomized SVD algorithm can be sensitive to the choice of the random matrix. Sample use case that resulted in challenge 1. Using a random matrix with a poor distribution of singular values can lead to inaccurate results. Fixes to challenge 1. Using a random matrix with a more uniform distribution of singular values can help to improve the accuracy of the algorithm. Challenge 2. The randomized SVD algorithm can be computationally expensive for very large matrices. Sample use case that resulted in challenge 2. Computing the SVD of a matrix with millions of rows and columns can take a long time. Fixes to challenge 2. Using a distributed computing framework, such as Apache Spark, can help to speed up the computation. sklearn, utils, xtmart, fastlogday. Description. The fastlogday function in Scikit-learn's xtmart module is designed to efficiently calculate the log determinant of a square matrix, particularly for large matrices. It utilizes a combination of Kolsky decomposition and a stable log sum express technique to achieve accuracy and computational efficiency. Inputs. A square numpy array representing the matrix for which the log determinant is to be calculated. Outputs. Logday, a scalar value representing the natural logarithm of the determinant of the input matrix A. Steps. Kolsky decomposition. The function first attempts to decompose the input matrix A into its Kolsky factorization, resulting in a lower triangular matrix L such that ALLT. This decomposition is particularly efficient for positive definite matrices, which are common in many applications. Log sum express. Once the Kolsky decomposition is obtained, the function calculates the logarithm of the diagonal elements of L. The log sum express technique is then applied to these logarithms, ensuring numerical stability, especially when dealing with very large or small values. Metrics. Computational efficiency. The fastlogday function is designed to be computationally efficient, particularly for large matrices. It utilizes optimized algorithms for Kolsky decomposition and log sum express, minimizing the number of operations required. Numerical stability. The log sum express technique employed in the algorithm ensures that the calculation of the log determinant is numerically stable, mitigating issues that can arise from very small or large values in the matrix. Visualization plots. Heat map of log determinant values. A heat map visualization can be created to display the log determinant values for different input matrices, allowing for the observation of patterns and trends in the results. Fine-tune parameters. None. The fastlogday function does not have any tunable parameters. Uncertainty methods. None. The fastlogday function does not provide any uncertainty estimates or confidence intervals. Challenges and fixes. Non-positive definite matrices. Sample use case when the input matrix A is not positive definite, e.g. it has negative eigenvalues or is singular. The Kolsky decomposition may fail. Fixes. SVD decomposition if Kolsky decomposition fails. Alternative decompositions such as singular value decomposition (SVD) can be used to calculate the determinant. However, these alternatives might be less efficient. Regularization, adding a small positive value to the diagonal of the matrix, can sometimes make it positive definite, allowing Kolsky decomposition to succeed. Numerical instability. Sample use case in cases where the input matrix contains very large or small values. The computation of the log determinant might suffer from numerical instability, leading to inaccurate results. Fixes. Log sum express technique. The fastlogd function incorporates the log sum express technique to address numerical instability. This technique involves combining logarithms in a way that mitigates the effects of large or small values. Scaling the input matrix dividing by a large constant can help to reduce the magnitude of elements, improving numerical stability. sklearn, utils, xstmart, density. Description. The density function from Scikit learns utils, xstmart module calculates the density of a given array. Density is defined as the number of non-zero elements divided by the total number of elements in the array. It provides a measure of sparsity, indicating the proportion of non-zero values in the array. Inputs. X, a numpy array representing the data for which density is to be calculated. Outputs. Density, a float value representing the calculated density of the input array. Steps. Calculate the number of non-zero elements in the input array using NP, count non-zerox. Calculate the total number of elements in the array using xsize. Divide the number of non-zero elements by the total number of elements to obtain the density. Metrics. Sparsity. The density value can be interpreted as a measure of sparsity. A higher density value indicates a denser array with more non-zero elements, while a lower value indicates a sparser array with more zero elements. Visualization plots. None density is a scalar value and doesn't lend itself to direct visualization. You might visualize the distribution of non-zero values in the array using histograms or other suitable plots. Fine-tune parameters. None. The function does not have any tunable parameters. Uncertainty methods. None density is a deterministic calculation and does not involve probabilistic elements. Challenges and fixes. None. There are no known challenges or fixes associated with the density function. sklearn, utils, xstmart, weighted mode. Description. This function calculates the weighted mode of a sequence of values. The weighted mode is the value that appears most often in the sequence, taking into account the weights associated with each value. The function can handle both numerical and categorical values. Inputs. A1D array of values for which to calculate the mode. Weights. An array of weights associated with each value in a. If none, all values are assumed to have equal weights. Outputs. Mode. The weighted mode of the sequence A. Count the number of times the mode appears in the sequence A, taking into account the weights. Steps. If weights is none, all values are assumed to have equal weights and the mode is calculated using the standard mode. Function. If weights is not none, the function iterates through each unique value inner and calculates the total weight associated with that value. The value with the highest total weight is returned as the weighted mode. Metrics. Accuracy. The accuracy of the weighted mode can be measured by comparing the predicted mode to the actual mode of the sequence. Visualization plots. Histogram. A histogram can be used to visualize the distribution of values in a and the corresponding weights. Bar chart. A bar chart can be used to compare the counts of different values in a, taking into account the weights. Fine-tune parameters. None. Uncertainty methods. Confidence interval. A confidence interval can be calculated for the weighted mode to indicate the uncertainty in the prediction. Challenges and fixes. Challenge 1. If the weights are not normalized, the weighted mode may be biased towards values with higher weights. Sample use case that resulted in challenge 1. If the weights represent the frequency of each value in a dataset, but the dataset is not balanced, the weighted mode may be skewed towards the majority class. Fixes to challenge 1. Normalize the weights before calculating the weighted mode. Challenge 2. If the sequencer contains duplicate values, the weighted mode may not be unique. Sample use case that resulted in challenge 2. If a dataset contains multiple instances of the same value, the weighted mode may be ambiguous. Fixes to challenge 2. Use a tie-breaking mechanism to select a single weighted mode from among the multiple values with the highest total weight. sklearn, utils, sparsefinks. Description. The sklearn, utils, sparsefinks module provides utilities for working with sparse matrices in scikit-learn. It offers functions for efficiently performing operations on sparse data, such as converting between sparse formats, calculating norms, and performing element-wise operations. Inputs. Sparse matrices. These can be in various formats supported by scikit-learn, like CSR, CSC, COO, etc. Dense matrices. In some cases, dense matrices can be provided as input, but operations will be optimized for sparse data. Outputs. Sparse matrices. The output is typically another sparse matrix in the desired format, depending on the function used. Dense matrices. In some functions, the output can be a dense matrix for specific computations. Scalars. Some functions return scalar values, like norms or element-wise sums. Steps. Data conversion. The functions often handle conversions between different sparse formats to optimize specific operations. Element-wise operations. Operations like addition, subtraction, or multiplication can be performed efficiently on sparse data. Norm calculations. Functions for computing various matrix norms are provided for sparse matrices. Metrics. Execution time. The efficiency of sparse operations is measured by the time taken for computation. Memory usage. Sparse data representations help reduce memory consumption compared to dense matrices. Visualization plots. Sparsity patterns. Visualizing the sparsity patterns of matrices can help understand the distribution of non-zero elements. Fine-tune parameters. Access. Some functions allow specifying the axis along which the operation is performed, e.g., row-wise or column-wise. D-type. Data type of the output array can be specified to control precision. Uncertainty methods. Any uncertainty methods are not directly related to sparse data manipulation in this module. Challenges and fixes. Challenge 1. Handling large sparse matrices with limited memory. Sample use case that resulted in challenge 1. Processing very large sparse matrices that exceed available memory. Fixes to challenge 1. Using efficient sparse formats. Choosing the appropriate sparse format CSR, CSC based on the operation can minimize memory overhead. Chunking. Divide the matrix into smaller chunks and process them iteratively, reducing memory demands. Challenge 2, optimizing performance for specific operations. Sample use case that resulted in challenge 2, performing complex operations on sparse matrices where efficiency is crucial. Fixes to challenge 2. Leverage specialized libraries. Explore libraries like Scikit, sparse for highly optimized sparse matrix operations. Use vectorized operations. Utilizing vectorized operations provided by NumPy and SciPy can significantly improve performance. Parallelization. Employ techniques like multi-threading or distributed computing to parallelize computations for further speed up. sklearn, utils, sparseFinks, incremean variance axis. Description. The incremean variance axis function is used to incrementally calculate the mean and variance of a sparse matrix along a specified axis. It efficiently updates the mean and variance as new data is added. This is particularly useful when dealing with large datasets that cannot fit entirely in memory, allowing for efficient processing in batches. Inputs. X, a sparse matrix representing the data. This matrix should be in a format supported by scikit-learn, such as CP, sparse, CSR matrix. Axis, an integer specifying the axis along which to calculate the mean and variance. 0 represents the rows, and 1 represents the columns. Last n, an optional integer specifying the number of previous data points to consider when calculating the mean and variance. This is useful for handling scenarios where the data has time-dependent characteristics and you want to focus on recent observations. Means, an optional array representing the current mean of the data along the specified axis. If none, the mean is initialized with zeros. Variance is an optional array representing the current variance of the data along the specified axis. If none, the variance is initialized with zeros. Sample weights, an optional array representing the weights assigned to each sample in the data. This allows for weighted calculations of the mean and variance, which can be useful for handling imbalanced datasets or datasets with varying levels of confidence. In the samples. Outputs. Means, an array representing the updated mean of the data along the specified axis. Variances, an array representing the updated variance of the data along the specified axis. Steps. Initialize the mean and variance based on the provided input arrays or set to 0 if not provided. Iterate over the data in batches if last n is specified. Calculate the sum of the data along the specified axis. Update the mean and variance using the sum, the number of data points, and the current mean and variance values. Metrics. Accuracy. The accuracy of the calculated mean and variance can be assessed by comparing them to the true mean and variance calculated over the entire dataset. Efficiency. The efficiency of the incremental calculation can be measured by comparing the time taken to calculate the mean and variance incrementally versus calculating them directly on the entire dataset. Visualization plots. Scatter plot. A scatter plot showing the relationship between the original data and the calculated mean and variance. Histogram. A histogram showing the distribution of the data and the calculated mean and variance. Fine-tune parameters. Last n. Adjusting the value of last n allows for controlling the window size used for calculating the mean and variance. A larger value will consider more previous data points, while a smaller value will focus on recent data. Sample weights. Fine-tuning. The sample weights can be used to adjust the influence of individual data points in the calculation of the mean and variance. This can be helpful in cases where certain data points are more reliable or have higher significance than others. Uncertainty methods. Confidence intervals. Calculate confidence intervals for the mean and variance to quantify a uncertainty in the estimated values. Challenges and fixes. Challenge 1. Numerical instability when handling very large datasets or data with extreme values. Numerical instability can occur, resulting in inaccurate mean and variance calculations. Sample use case that resulted in challenge 1. Working with datasets with very large values or datasets with a wide range of values. Fixes to challenge 1. Use numerical stability techniques such as using a stable mean and variance calculation algorithm, or scaling the data to a smaller range. Challenge 2. Memory constraints when dealing with very large datasets. Loading the entire dataset into memory may not be feasible. Sample use case that resulted in challenge 2. Datasets that are too large to fit in memory, requiring processing in batches. Fixes to challenge 2. Use the incremental calculation feature of the function, processing the data in batches to avoid memory overload. sklearn, utils, sparse finks, in-place column scale. Description. This function performs in-place column scaling on a sparse matrix. It scales each column of the matrix by dividing each element in the column by the maximum absolute value in that column. This can be useful for preprocessing sparse data before applying machine learning algorithms that are sensitive to feature scaling. Inputs. X. This is the sparse matrix that needs to be scaled. It should be a SCP, sparse matrix. Scale. This is an optional array that specifies the scaling factor for each column. If not provided, the scaling factor for each column will be calculated as the maximum absolute value in that column. Outputs. X. This is the modified sparse matrix with scaled columns. The original matrix is modified in place. Steps. The function first calculates the maximum absolute value in each column of the sparse matrix. It then divides each element in each column by the corresponding maximum absolute value. The function modifies the original matrix in place, so no new matrix is returned. Metrics. None. The function does not calculate any metrics. It simply performs the scaling operation. Visualization plots. None. No visualization plots are associated with this function. Fine-tune parameters. Scale. This parameter allows you to specify the scaling factor for each column manually. You can use this to adjust the scaling based on your specific requirements. Uncertainty methods. None. No uncertainty methods are directly associated with this function. Challenges and fixes. Challenge 1. Sample use case that resulted in challenge 1. If the sparse matrix contains columns with all zeros, the scaling factor for those columns will be 0, leading to division by 0 errors. Fixes to challenge 1. You can handle this by either replacing the zeros in the scaling factor array with a small positive value, e.g., 1e10, or by removing the columns with all zeros from the sparse matrix before scaling. Challenge 2. Sample use case that resulted in challenge 2. If the sparse matrix contains columns with very large values, the scaling factor for those columns can be extremely small, leading to numerical instability. Fixes to challenge 2. To mitigate this, you can consider using a different scaling method, such as standardization, which scales each column to have 0 mean and unit variance. sklearn, utils, sparse finks, in-place row scale. Description. This function scales each row of a sparse matrix by a given vector. The scaling is done in place, meaning that the original matrix is modified. Inputs. X a sparse matrix, where rows are samples and columns are features. Rosums a vector of the same length as the number of rows in X, containing the sum of each row. Outputs. X the scaled sparse matrix. Rosums the row sums used for scaling. Steps. The function iterates over each row in the sparse matrix. For each row, the function multiplies each non-zero element by the corresponding element in the rosums vector. The function updates the sparse matrix with the scaled values. Metrics. None. Visualization plots. None. Fine-tune parameters. None. Uncertainty methods. None. Challenges and fixes. Challenge 1. Dividing by 0 errors can occur if the rosums vector contains 0 values. Sample use case that resulted in challenge 1 when a row in the input sparse matrix has all 0 values. The corresponding rosum will also be 0. Dividing by 0 during scaling will result in an error. Fixes to challenge 1. Replace 0 values in rosums with a small non-zero value like 1e10. Challenge 2. Memory errors can occur if the sparse matrix is very large. Sample use case that resulted in challenge 2. Working with very large sparse matrices, especially with many non-zero elements, can lead to memory issues during scaling. Fixes to challenge 2. Consider using a more efficient sparse matrix format like compressed sparse row CSR or compressed sparse column CSC. For extremely large matrices, consider scaling the rows in batches to reduce memory pressure. sklearn, utils, sparsefinks, in-place swap row. Description. The in-place swap row function swaps 2 rows of a sparse matrix in place. This function is efficient and avoids unnecessary data copying. It's particularly useful for manipulating sparse matrices without compromising performance. Inputs. X a sparse matrix represented in CSR format. This is the input matrix that needs to be modified. I an integer representing the index of the first row to be swapped. J an integer representing the index of the second row to be swapped. Outputs. X the input sparse matrix with the specified rows swapped in place. No separate output is returned. Steps. The function directly manipulates the internal data structures of the CSR matrix to swap the rows efficiently. It performs the swap by modifying the indices, data, and indptr arrays of the CSR matrix. Metrics. Time complexity. The time complexity is 1 where n is the number of non-zero elements in the 2 rows being swapped. This makes it efficient for sparse matrices with a low density of non-zero values. Space complexity. The space complexity is O1 as the function operates in place and doesn't require any additional memory for the swap operation. Visualization plots. Scatter plot. Visualizing the data points in the rows before and after the swap can help understand the transformation. Heatmap. A heat map representation of the sparse matrix before and after the swap can provide a visual understanding of the row changes. Fine-tune parameters. There are no parameters to fine-tune in this function. Uncertainty methods. There are no inherent uncertainties in this function as it performs a deterministic swap operation. Challenges and fixes. Challenge 1. Attempting to swap rows with indices beyond the matrix dimensions. Sample use case that resulted in challenge 1. Trying to swap rows with indices greater than or equal to the number of rows in the matrix. Fixes to challenge 1. Validate the input indices I and j to ensure they are within the valid range of row indices 0 to number of rows 1 before performing the swap. Raise an index error if the indices are invalid. Challenge 2. Handling invalid input types for the matrix or indices. Sample use case that resulted in challenge 2. Passing a dense matrix instead of a sparse CSR matrix. Or providing indices that are not integers. Fixes to challenge 2. Check the type of the input matrix X to ensure it's a CSR matrix using isInstance X. SCIP, sparse, CSR matrix. Validate the data type of the input indices I and j to ensure they are integers. If they are not, raise a type error. sklearn, utils, sparse finks, in-place swap column. Description. This function swaps two columns in a sparse matrix in place. Modifying the matrix directly. It modifies the sparse matrix by swapping the column indices specified by the user. Inputs. X a sparse matrix. The input sparse matrix containing the columns to be swapped. Call 1 an integer representing the index of the first column to swap. Call 2 an integer representing the index of the second column to swap. Outputs. None. This function modifies the input sparse matrix in place and does not return any value. Steps. The function obtains the column indices of the sparse matrix. It then finds the indices corresponding to the two columns to be swapped. Finally, it swaps the values of the two columns in the sparse matrix by exchanging the corresponding indices. Metrics. Time complexity ons, where n and zx is the number of non-zero elements in the sparse matrix. Visualization plots. Scatter plot of the original sparse matrix and the modified matrix after swapping the columns. Can be helpful to visualize the changes. Fine-tune parameters. No fine-tuning parameters are available for this function. Uncertainty methods. Not applicable. Challenges and fixes. Challenge 1. If the specified column indices are invalid, e.g., out of bounds, it will raise an index error. Sample use case that resulted in challenge 1 in place swap column X. 5. 10 where the input matrix has only 5 columns. Fixes to challenge 1 ensure that the provided column indices are valid and within the bounds of the sparse matrix. Challenge 2. If the input matrix is not a sparse matrix, the function will raise a type error. Sample use case that resulted in challenge 2 in place swap column NP. Array 1, 2, 3, 4. 0, 1. Fixes to challenge 2 make sure the input matrix is a sparse matrix from libraries like SCIP, sparse. sklearn, utils, sparse finks, mean variance access. Description. This function computes the mean and variance of a sparse matrix along a given axis. It leverages the efficiency of sparse matrix operations to avoid unnecessary calculations on zero elements. Inputs. X a sparse matrix of shape n samples. N features. Axis an integer representing the axis to calculate mean and variance along. 0 for row-wise sample-wise calculations and 1 for column-wise feature-wise calculations. Outputs. Mean an array containing the mean values along the specified axis. Variance an array containing the variance values along the specified axis. Steps. Calculate the mean of the non-zero elements along the specified axis. Calculate the squared mean of the non-zero elements along the specified axis. Calculate the sum of the squared non-zero elements along the specified axis. Calculate the variance using the formula variance sum of squared non-zero elements, n non-zeros. Squared mean. Metrics. Efficiency. This function efficiently computes the mean and variance by exploiting sparsity. Accuracy. The computed mean and variance are accurate for sparse matrices. Visualization plots. Scatter plot visualize the distribution of values along the specified axis with mean and variance. Highlighted. Histogram plot the histogram of values along the specified axis with mean and variance indicated. Fine-tune parameters. Axis. The choice of axis determines the direction of the calculation rows or columns. Uncertainty methods. Confidence intervals. Calculate the confidence intervals for the mean and variance using statistical methods. Bootstrap. Resample the data multiple times and calculate the mean and variance for each resample. To estimate the uncertainty. Challenges and fixes. Challenge 1. Handling very sparse matrices with a small number of non-zero elements. Sample use case that resulted in challenge 1 is sparse matrix with a high sparsity level where the number of non-zero elements is significantly less than the total number of elements. Fixes to challenge 1. Use appropriate data structures and algorithms that are optimized for handling sparse data. Consider using alternative methods for computing mean and variance if the sparsity is extremely high. Challenge 2. Numerical instability for matrices with very large values. Sample use case that resulted in challenge 2 a sparse matrix with extremely large values in some of the non-zero elements. Fixes to challenge 2. Normalize the data before computing mean and variance to avoid overflow issues. Use numerical methods that are more robust to large values. sklearn, utils, sparse finks, in-place column scale. Description. This function performs in-place scaling of columns in a sparse CSR matrix. It divides each column by its maximum value, effectively scaling the column values to the range 0, 1. Inputs. X. A sparse CSR matrix, representing the data to be scaled. Copy a Boolean flag. If true, a copy of the input matrix is created and scaled. If false, the scaling is performed in place on the original matrix. Outputs. X. The input sparse CSR matrix, modified in place if copy is false. If copy is true, a new scaled sparse CSR matrix is returned. Steps. If copy is true, a copy of the input matrix is created. For each column in the matrix, the maximum value in the column is calculated. The column is divided by the maximum value. Metrics. None. This function is a data pre-processing step and doesn't directly measure performance. Visualization plots. None. No direct visualization plots are produced by this function. Fine-tune parameters. Copy controls whether a copy of the input matrix is created true or scaling is performed in place. False. Uncertainty methods. None. This function does not involve any uncertainty estimation. Challenges and fixes. Challenge 1. Dividing by 0 if a column contains only zeros. Sample use case that resulted in challenge 1 a dataset with a column containing all zero values. Fixes to challenge 1. The function handles this case by skipping the scaling of columns with all zeros. Challenge 2. None. Sample use case that resulted in challenge 2. None. Fixes to challenge 2. None. sklearn, utils, sparsefinks fast. Description. The sparsefinks fast module provides fast implementations of common sparse matrix operations that are optimized for performance. It includes functions for performing operations such as dot products, matrix multiplication, and element-wise operations on sparse matrices. Inputs. Sparse matrix. A sparse matrix representation, typically a SCP, sparse matrix, such as CSR matrix or CSC matrix. This represents a matrix where most elements are zero, and only the non-zero elements are stored efficiently. Dense array. A dense array like a NumPy array that can be used in operations with the sparse matrix. Outputs. Sparse matrix. The resulting sparse matrix after applying the operation. Dense array. The resulting dense array after applying the operation. Steps. Preprocessing. The functions often involve preprocessing the input sparse matrices, e.g., converting to a specific format like CSR for efficient computations. Optimized operations. The core of these functions implements highly optimized algorithms to perform the specified operations on sparse matrices, often using Python or other optimized libraries for speed. Metrics. Time complexity. The functions are designed to have efficient time complexity, especially for large sparse matrices. Memory efficiency. They aim to minimize memory usage by taking advantage of the sparsity of the input matrices. Visualization plots. Not directly applicable. The focus of these functions is on efficient computation rather than visualization. Visualization would likely be done on the resulting data from these operations. Fine-tune parameters. Not applicable. The functions in sparseFinks fast are typically designed to be used directly with minimal or no tunable parameters. Uncertainty methods. Not applicable. The functions in sparseFinks fast are focused on deterministic operations and do not directly involve uncertainty methods. Challenges and fixes. Challenge 1. Large sparse matrix handling. Handling very large sparse matrices can lead to memory limitations. Sample use case that resulted in challenge 1. Processing a sparse matrix with billions of non-zero elements. Fixes to challenge 1. Use a sparse matrix format optimized for efficient memory storage, e.g., CSR for row-wise access. Employ out-of-core techniques to process data in chunks if the matrix does not fit entirely in memory. Challenge 2. Performance optimization. Achieving optimal performance requires choosing the right sparse matrix format and algorithms for the specific operations being performed. Sample use case that resulted in challenge 2. A sparse matrix multiplication operation taking significantly longer than expected. Fixes to challenge 2. Profile the code to identify performance bottlenecks. Consider using more optimized sparse matrix libraries or algorithms if possible, e.g., BLAS optimized implementations. Experiment with different sparse matrix formats, CSR, CSC, to see which performs better for the specific operation. sklearn, utils, sparseFinks fast and place CS row normalizer 1. Description. This function normalizes the rows of a CSR matrix in place using the L1 norm. This means that for each row, the values are divided by the sum of their absolute values. This results in each row having a unit L1 norm sum of absolute values equals 1. Inputs. X. A CSR matrix representing the input data. Copy a Boolean value indicating whether to copy the input matrix before normalization. If true, a copy is created and modified, leaving the original matrix untouched. If false, the normalization is performed in place on the original matrix. Outputs. X. The CSR matrix with normalized rows. If copy is true, this is a modified copy of the original matrix. If copy is false, this is the original matrix, modified in place. Steps. Calculate the sum of absolute values for each row in the input CSR matrix. Divide each element in the matrix by the corresponding row sum. Metrics. L1 norm. This can be used to verify that all rows have a unit L1 norm after normalization. Visualization plots. Heat map. A heat map of the normalized matrix can be visualized to show the distribution of values across rows and columns. Fine-tune parameters. Copy. This parameter allows you to control whether the normalization is performed in place on the original matrix or on a copy. Setting copy to true ensures that the original matrix remains untouched. Uncertainty methods. None. This function does not involve any uncertainty estimation. Challenges and fixes. Challenge 1. 0 row sum. If a row in the input matrix has all zeros, dividing by its row sum will result in division by 0, leading to an error. Sample use case that resulted in challenge 1. A matrix with a row containing only zeros. Fixes to challenge 1. Handle 0 row sums by skipping normalization for those rows. Set the normalized values to 0 for rows with all zeros. Challenge 2. Numerical instability in extreme cases. The sum of absolute values for a row might be very large or very small, leading to numerical instability during the normalization process. Sample use case that resulted in challenge 2. A matrix with very large or very small values. Fixes to challenge 2. Use robust numerical algorithms to avoid numerical instability. Scale the values before normalization to reduce the potential for large or small row sums. sklearn, utils, sparseFinks fast and place CS row normalizer 2. Description. This function performs L2 normalization of rows in a sparse CSR matrix in place, modifying the original matrix. L2 normalization scales each row of the matrix so that the Euclidean norm length of each row is equal to 1. This is commonly used in machine learning to prevent features with larger magnitudes from dominating the learning process. Inputs. X. A sparse CSR matrix. It represents the input data where each row corresponds to a data point and each column represents a feature. Outputs. X. The modified CSR matrix, where each row is normalized by its L2 norm. Steps. Calculate the L2 norm of each row in the CSR matrix. Divide each element in each row by its corresponding row's L2 norm. This effectively scales each row to have a unit length. Metrics. L2 norm of each row. The L2 norm of each row in the output matrix is 1. Visualization plots. Scatter plot of data points before and after normalization. This plot shows the impact of normalization on the distribution of data points in the feature space. Fine-tune parameters. None. This function has no tunable parameters. Uncertainty methods. None. This function does not involve uncertainty estimation. Challenges and fixes. Challenge 1. Numerical instability can occur if a row has a very small or 0 L2 norm, leading to division by 0. Sample use case that resulted in challenge 1. A data point with all feature values equal to 0. Fixes to challenge 1. Handle 0 norm rows. The function should include a check for 0 norm rows and handle them appropriately. For example, by assigning them a default value, e.g., a vector of zeros. Challenge 2. The in-place modification of the input matrix might not be desirable in some scenarios, where the original matrix needs to be preserved. Sample use case that resulted in challenge 2. When multiple operations need to be performed on the same data and the original representation is required for subsequent steps. Fixes to challenge 2. Create a copy. The function should provide an option to create a copy of the input matrix before performing normalization, ensuring that the original matrix remains unchanged. sklearn utils graph. Description. The sklearn utils module in Scikit-learn provides various utility functions that are helpful for data preprocessing, model selection, and general data manipulation tasks. These utilities simplify common operations and enhance the workflow in machine learning projects. Inputs. Data. This refers to the dataset that you want to analyze or train your machine learning models on. The data can be in various formats like NumPy arrays, pandas data frames, or lists. Parameters. These are the configuration settings for the utility functions. They control aspects like the behavior of the function, specific algorithms, or thresholds for various operations. Outputs. Processed data. The output of many utilities is transformed data. For instance, data standardization, encoding categorical features, or splitting data into training and testing sets. Statistics or insights. Certain utilities provide summary statistics, such as feature importance or the results of hypothesis tests, which offer insights into the data. Model selection results. Some utilities help in selecting the best model from a set of candidate models by evaluating their performance on the data. Steps. Data preprocessing. This involves cleaning, transforming, and preparing the data for use in machine learning models. Common preprocessing steps include handling missing values, imputing missing data using techniques like mean imputation, median imputation, or model-based imputation. Feature scaling. Scaling features to a common range, e.g., 0 to 1 or -1 to 1 using techniques like standardization or normalization. Encoding categorical features. Converting categorical features into numerical representations, using methods like one-hot encoding or ordinal encoding. Model selection. These utilities help in choosing the best model from a set of candidate models. Common techniques include cross-validation. This technique splits the data into multiple folds and trains the model on different combinations of folds to estimate its generalization performance. Grid search. This method systematically searches over a predefined range of hyperparameter values to find the optimal configuration for the model. Metrics. Performance metrics depending on the task classification or regression. These utilities might provide metrics like accuracy, precision, recall, F1 score, AUC, or mean squared error MSE. Feature importance. For certain models, utilities can calculate feature importance, which indicates the relative contribution of each feature to the model's predictions. Visualization plots. Scatter plots. Visualizing the relationship between features in the dataset. Histograms showing the distribution of features. Pair plots. Creating pairwise scatter plots of all features in the dataset. Confusion matrix. Representing the performance of a classification model by showing true positives, true negatives, false positives, and false negatives. Fine-tune parameters. Scaling parameters for standardization and normalization. Parameters like mean and STD can be adjusted based on the data distribution. Encoding parameters. Parameters for one-hot encoding, ordinal encoding, or other encoding methods might specify the number of features to be created. Model selection parameters. Hyperparameters for cross-validation techniques like k-number of folds, or parameters for grid search like the range of hyperparameter values to explore. Uncertainty methods. Confidence intervals. Estimating the range of possible values for a parameter or prediction, providing a sense of the uncertainty associated with the estimate. Bootstrap resampling. Generating multiple datasets by sampling with replacement from the original data to assess the variability of model predictions. Challenges and fixes. Challenge 1. Missing data. Missing data can lead to biased models or inaccurate predictions. Sample use case. A dataset with missing values for income levels might result in inaccurate Predictions for loan applications. Fixes. Imputation techniques impute missing values using methods like mean imputation, median imputation, or more sophisticated techniques like KNN imputation or model-based imputation. Challenge 2. Imbalanced datasets. When the classes in a classification problem have significantly different frequencies, models can be biased towards the majority class. Sample use case. A dataset for fraud detection might have a very low percentage of fraudulent transactions, leading to models that are not effective at identifying fraud. Fixes. Oversampling. Replicate minority class samples to increase their representation in the dataset. Undersampling. Reduce the number of majority class samples to balance the dataset. Class weights. Assign different weights to different classes during model training to penalize misclassifications of minority class samples more heavily. Challenge 3. Data leakage. When information from the testing set is inadvertently used during model training, it can lead to overly optimistic performance estimates. Sample use case. If features from the target variable are included in the training dataset, the model might learn spurious relationships and perform poorly on unseen data. Fixes. Data splitting. Carefully split the data into training and testing sets before performing any data transformations or feature engineering. Feature engineering. Only use features that are available at the time of prediction when building models. Challenge 4. High dimensionality datasets with a large number of features can lead to overfitting and computational challenges. Sample use case. A dataset with thousands of features might lead to a model that performs well on the training data but generalizes poorly to new data. Fixes. Feature selection. Identify and select the most relevant features for the task, reducing the dimensionality of the dataset. Dimensionality reduction techniques. Apply techniques like principal component analysis (PCA) or TSNE to reduce the dimensionality of the dataset while preserving important information. sklearn, utils, graph, single source shortest path length. Description. This function calculates the shortest path lengths from a single source node to all other nodes in a graph represented by an adjacency matrix. Inputs. Adjacency matrix. A 2D array representing the adjacency matrix of the graph. The element at index I, j indicates the weight of the edge connecting node I to node j. A value of 0 indicates no edge. Source. The index of the source node from which the shortest paths are calculated. Outputs. Distances. A 1D array containing the shortest path lengths from the source node to all other nodes. The element at index I represents the shortest path length from the source node to node I. Steps. The algorithm initializes all distances to infinity except for the source node, which has a distance of 0. It then iteratively updates the distances of neighboring nodes by checking if the current distance to the neighbor is shorter than the shortest path length currently known. This process continues until all nodes have been visited or no further distance improvements are possible. Metrics. Number of edges traversed. The total number of edges traversed during the path computation. Average path length. The average length of the shortest paths from the source node to all other nodes. Visualization plots. Graph visualization with shortest path highlighted. Visualize the graph with edges corresponding to the shortest paths highlighted in a different color. Distance distribution plot. A histogram or density plot showing the distribution of shortest path lengths from the source node to all other nodes. Fine-tune parameters. None. Uncertainty methods. None. Challenges and fixes. Challenge 1. The function assumes the graph is undirected. Sample use case that resulted in challenge 1 using the function on a directed graph could result in incorrect shortest path lengths as it does not consider the directionality of edges. Fixes to challenge 1 for directed graphs. Consider using a different shortest path algorithm that specifically handles directed edges, such as the Dijkstra's algorithm. Challenge 2. The function assumes the graph has no negative weights. Sample use case that resulted in challenge 2 applying the function on a graph with negative edge weights could lead to incorrect shortest path lengths as the algorithm assumes non-negative weights. Fixes to challenge 2 for graphs with negative weights. Use alternative algorithms such as the Bellman-Ford algorithm, which can handle negative weights. sklearn, utils, random, sample without replacement. Description. This function generates a random sample without replacement from a given population. It uses the Fisher-Yates shuffle algorithm to efficiently generate a sample without duplicates. Inputs. N samples the number of samples to generate. This value must be less than or equal to the size of the population. NP population, the size of the population from which to sample. Outputs. Sample a NumPy array containing the random sample without replacement. The sample will have a length equal to n samples. Steps. Generate a list of integers representing the population. Shuffle the list using the Fisher-Yates shuffle algorithm. Extract the first n samples elements from the shuffled list. Return the extracted elements as a NumPy array. Metrics. Time complexity on, where n is the size of the population. Visualization plots. Histogram of the sampled values. Fine-tune parameters. N samples adjust the number of samples to generate based on your specific needs. Uncertainty methods. Since the function relies on a random shuffle, the uncertainty is inherent in the random sampling process. Challenges and fixes. Challenge 1. The function may return an empty array if n samples is greater than NP population. Sample use case that resulted in challenge 1. You try to generate a sample of 10 elements from a population of 5. Fixes to challenge 1. Ensure that n samples is always less than or equal to NP population. Challenge 2. The function may not be efficient for extremely large populations. Sample use case that resulted in challenge 2. You are working with a very large dataset and need to generate a sample of millions of elements. Fixes to challenge 2. Consider using alternative sampling methods like reservoir sampling, which can be more efficient for large populations. sklearn, utils, arrayFun.cs. Description. The sklearn, utils, arrayFun.cs module provides utility functions for working with arrays, particularly in the context of machine learning. These functions are designed to simplify common array manipulation tasks and ensure consistency across scikit-learn's functionalities. Inputs. Input 1. Arrays. The primary input for these functions is typically one or more NumPy arrays, representing data in various forms, e.g., feature vectors, target values, etc. Outputs. Output 1. Transformed arrays. The outputs of these functions are often modified versions of a input arrays, either reshaped, filtered, or otherwise manipulated for specific machine learning purposes. Steps. Step 1. Data preparation. The functions might involve initial pre-processing steps like converting data types, handling missing values, or normalizing data. Step 2. Array manipulation. Core operations on the input arrays, such as resizing, sorting, or applying specific mathematical transformations. Metrics. Metric 1 Computational efficiency. The functions are often optimized for performance, aiming to minimize the computational cost of array operations. Metric 2 Data integrity, ensuring that the manipulation of arrays does not introduce errors or inconsistencies in the data. Visualization plots. Visualization plot 1 Scatter plots for visualizing relationships between features in a dataset. Visualization plot 2 Histograms for understanding the distribution of features or target variables. Fine-tune parameters. Parameter 1 Axis for specifying the axis or axes along which operations are performed, e.g. for sorting or summing. Parameter 2 Order for specifying the sorting order, ascending or descending. Uncertainty methods. Uncertainty method 1 Confidence intervals, calculating confidence intervals for statistical estimates derived from the data. Uncertainty method 2 Bootstrap resampling, using resampling techniques to assess the variability of results. Challenges and fixes. Challenge 1 Handling missing values. Dealing with missing or incomplete entries in arrays can lead to errors or biased results. Sample use case that resulted in Challenge 1 attempting to perform calculations on an array containing non-values. Fixes to Challenge 1 Imputation techniques, such as replacing missing values with the mean, median, or other appropriate values. Challenge 2 Data type conversion, ensuring that data is represented using the correct data types, e.g., integers, floats, strings, is crucial for consistent computations. Sample use case that resulted in Challenge 2 performing arithmetic operations on arrays with incompatible data types. Fixes to Challenge 2 explicitly casting data to the desired types using functions like astype, sklearn, utils, arrayFun.cs, minpos. Description. The minpos function is used to efficiently find the index of the minimum value in a NumPy array or a sparse matrix. Inputs. The input array or sparse matrix where the minimum value needs to be found. It can be a NumPy array, a SciPy sparse matrix, or any object with a min method and a shape attribute. Access. The axis along which to find the minimum value defaults to none, which finds the minimum across the flattened array. Out. An optional output array. If provided, the result will be stored in this array. Keep dims. If true, the output will have the same number of dimensions as the input, with the reduced axis retained as a singleton dimension. Defaults to false. Outputs. Minpos. A NumPy array containing the indices of the minimum values along the specified axis. Minval. A NumPy array containing the minimum values along the specified axis. Steps. The function iterates over the specified axis of the input array or sparse matrix. For each element, it compares it with the current minimum value. If the current element is smaller than the current minimum, it updates the minimum value and its corresponding index. Finally, it returns the indices and the minimum values. Metrics. Time complexity on, where n is the number of elements in the input array or sparse matrix. Space complexity O1 for the input array or sparse matrix, and om for the output array, where m is the number of minimum values. Visualization plots. Scatter plot showing the relationship between the input array or sparse matrix and the indices of the minimum values. Histogram showing the distribution of the minimum values. Fine-tune parameters. Access. The axis along which to find the minimum value. Out. An optional output array to store the result. Keep dims whether to retain the reduced axis as a singleton dimension in the output. Uncertainty methods. Not applicable for this function. Challenges and fixes. Challenge 1 Handling empty arrays or matrices. Sample use case that resulted in challenge 1 input array or matrix with 0 elements. Fixes to challenge 1. The function should handle empty arrays or matrices by returning an empty array for both the minimum values and their indices. Challenge 2. Handling non-values. Sample use case that resulted in challenge 2 input array or matrix containing non-values. Fixes to challenge 2. The function should ignore non-values and only consider valid numerical values when finding the minimum. sklearn, utils, metadata routing. Description. The metadata routing function in Scikit learn's utils module provides a mechanism to route metadata associated with various objects, such as estimators, transformers, and datasets, to ensure consistent and efficient data handling throughout the machine learning workflow. It facilitates the propagation of metadata, including information like input and output data types, dimensions, and scaling parameters, through different stages of a model pipeline. Inputs. Metadata. A dictionary like object containing key-value pairs representing metadata associated with an object, e.g., estimator. Dataset. Routing. A list of tuples, each tuple representing a routing rule. Each rule consists of a source key, a destination key, and a transformation function optional. The transformation function defines how the data associated with the source key should be processed before being routed to the destination key. Outputs. Transformed metadata. The original metadata object with the routed data values applied to the specified destination keys. Steps. Initialization. The function initializes an empty dictionary to store the transformed metadata. Routing loop. The function iterates through each routing rule specified in the routing parameter. Source value retrieval. The function extracts the value associated with the source key from the input metadata. Transformation. If a transformation function is specified in the routing rule, it applies the function to the extracted value. Destination value update. The function updates the transformed metadata dictionary with the processed value under the destination key. Metrics. Metadata consistency. The function helps maintain metadata consistency throughout the model pipeline, reducing the chances of errors due to incompatible data types or dimensions. Visualization plots. Data flow diagram. The metadata routing mechanism can be visualized as a data flow diagram, showcasing the movement of metadata through different stages of a model pipeline. Fine-tune parameters. Routing rules. The routing parameter allows fine-grained control over the routing process by defining specific source and destination keys and optional transformations. Uncertainty methods. Not applicable. Challenges and fixes. Challenge 1. Metadata mismatch. If the metadata associated with different stages of a model pipeline is inconsistent, e.g., different data types or dimensions, it can lead to errors or unexpected results. Sample use case. A model pipeline might have a feature scaling step that assumes numerical input data, but the subsequent estimator might expect categorical data. Fixes to challenge 1. Ensure that the metadata associated with each stage of the pipeline is consistent and reflects the actual data types and dimensions. Use tools like metadata routing to propagate metadata appropriately. Challenge 2. Metadata overriding. If multiple routing rules are specified for the same destination key, it can lead to overwriting of metadata, resulting in unexpected behavior. Sample use case. A routing rule might be defined to route a feature scaling parameter to a specific key, but another rule might overwrite this value with a different scaling parameter. Fixes to challenge 2. Ensure that routing rules are carefully defined to avoid conflicting Destination keys. Use a hierarchical approach to metadata organization to avoid overriding of essential metadata. YAML. sklearn, utils, metadata routing, get routing for object. Description. This function determines the appropriate routing for a given object within Scikit learns metadata system. Inputs. Object. The object whose routing needs to be determined. It can be an instance of a Scikit learn estimator, transformer, or any other object that has associated metadata. Is for typing a Boolean flag indicating whether the routing is being determined for type checking purposes. Outputs. Routing. A dictionary containing the routing information for the given object. This dictionary defines the key value pairs that will be used to access and manage metadata associated with the object. Steps. The function first checks if the object is an instance of a Scikit learn estimator or transformer. If it is, it uses the object's class name to construct the routing path. If the object is not an estimator or transformer, it tries to determine the routing based on the object's type and its attributes. The routing path is constructed by combining the object's class name, type, and relevant attributes. Metrics. None. Visualization plots. None. Fine-tune parameters. None. Uncertainty methods. None. Challenges and fixes. Challenge 1. Handling objects with complex inheritance hierarchies. Sample use case that resulted in challenge 1. An object that inherits from multiple Scikit learn classes, making it difficult to determine the correct routing. Fixes to challenge 1. The function uses a combination of class name, type, and attributes to ensure accurate routing even in complex inheritance scenarios. Challenge 2. Handling objects that do not have a well-defined type or class. Sample use case that resulted in challenge 2. Custom objects or objects from external libraries that do not inherit from Scikit learn classes. Fixes to challenge 2. The function allows for providing a custom routing path through the routing key argument. This enables users to define specific routing for objects that do not have predefined routing. sklearn utils metadata routing process routing. Description. The process routing function in sklearn utils metadata routing is a powerful tool for managing the flow of data and metadata within Scikit learn pipelines. It allows you to easily track and apply metadata transformations throughout your machine learning workflow. Inputs. Estimator. The estimator object to be processed. This can be any Scikit learn estimator, such as a classifier, regressor, or transformer. Data. The input data to be processed by the estimator. This can be a NumPy array, pandas data frame, or other data structure that is compatible with Scikit learn. Fit params. A dictionary of keyword arguments to be passed to the estimator's fit method. This can be used to specify hyperparameters or other options for the training process. Quags. Additional keyword arguments that can be passed to the process routing function. These arguments are passed through to the underlying fit and transform methods of the estimator. Outputs. Output data. The output data produced by the estimator's fit or transform method. The format of the output data will depend on the specific estimator used. Fitted estimator. The fitted estimator object. This object can be used to make predictions on new data. Steps. 1. Data and metadata routing. The process routing function first routes the input data and metadata through the estimator's fit or transform method. This ensures that the estimator is properly trained or transformed based on the input data. 2. Metadata transformation. The process routing function then automatically applies metadata transformations to the output data and fitted estimator. These transformations ensure that the metadata is consistent with the new data and that the estimator can be used correctly in downstream tasks. Metrics. Accuracy measures the proportion of correct predictions made by the estimator. Precision measures the proportion of true positives among all positive predictions. Recall measures the proportion of true positives among all actual positives. F1 score a harmonic mean of precision and recall. AUC area under the curve measures the performance of the estimator across all possible classification thresholds. Visualization plots. Confusion matrix, a visual representation of the classification results, showing the number of true positives, true negatives, false positives, and false negatives. ROC curve, a plot of the true positive rate against the false positive rate for different classification thresholds. Precision recall curve, a plot of the precision against the recall for different classification thresholds. Feature importance plot, a bar chart showing the relative importance of different features in the model. Fine-tune parameters. Regularization parameters controls the complexity of the model and prevents overfitting. Learning rate determines the size of the steps taken during optimization. Number of layers controls the depth of the neural network. Number of hidden units controls the width of the neural network. Activation functions defines the non-linearity of the model. Uncertainty methods. Confidence intervals estimates the uncertainty in the predictions by calculating the range of possible values. Bayesian inference uses probabilistic models to estimate the uncertainty in the model parameters. Dropout randomly drops out neurons during training to improve generalization. Challenges and fixes. Challenge 1: metadata inconsistencies between different data sources. Sample use case: combining data from a database and a CSV file, where the data types and column names may differ. Fixes. Metadata alignment: use the sklearn, utils, metadata routing module to ensure consistent metadata across all data sources. Data conversion: convert the data to a common format, such as a pandas data frame, to facilitate metadata handling. Challenge 2: handling missing values in the data. Sample use case: dealing with missing values in a dataset used for training a machine learning model. Fixes. Imputation: use imputation methods to fill in missing values with estimated values. Feature engineering: create new features that capture information about missing values. Model selection: choose models that are robust to missing values, such as decision trees. sklearn, utils, metadata routing, metadata router. Description: the metadata router class acts as a central hub for managing and propagating metadata within scikit-learn pipelines and transformers. It allows you to define and track information about your data, such as column names, data types, and other relevant characteristics, as it flows through different stages of your machine learning workflow. Inputs. Input 1: the metadata router itself. It initializes with the initial metadata dictionary, which can be populated with information about the data being processed. This dictionary holds key-value pairs where the keys are metadata keys and the values are metadata values associated with those keys. Outputs. Output 1: modified metadata as data passes through the pipeline. The metadata router can modify the metadata dictionary. This modification can occur based on the transformations applied by different pipeline stages. For example, if a feature scaling step is applied, the metadata might be updated to reflect the new scale of the features. Steps. Step 1: initialization. The metadata router is initialized with an empty metadata dictionary. This dictionary will store the metadata as data flows through the pipeline. Step 2: Metadata propagation. As data is processed by transformers in the pipeline, the metadata router intercepts and propagates metadata. It uses a set of predefined rules to determine how metadata should be transformed or modified based on the actions of each transformer. Metrics. Metric 1: There are no specific metrics directly associated with the metadata router itself. However, the metadata it manages can be used to derive metrics related to data quality or transformation. Effects. Visualization plots. Visualization plot 1: There are no specific visualization plots directly associated with the metadata router. However, the metadata it manages can be used to generate visualizations related to data distribution, feature characteristics, or other insights based on the metadata being tracked. Fine-tune parameters. Parameter 1: There are no specific fine-tuning parameters for the metadata router itself. The parameters are primarily controlled within the transformers and estimators that utilize the metadata router to manage metadata propagation. Uncertainty methods. Uncertainty method 1: There are no specific uncertainty methods associated with the metadata router. However, the metadata it manages can be used to perform uncertainty analysis on the predictions or estimations made by the models within the pipeline. Challenges and fixes. Challenge 1: Maintaining consistent metadata across pipeline stages. Ensuring that metadata is consistently updated and propagated throughout the pipeline can be challenging, especially when dealing with complex pipelines involving multiple transformers. This can lead to inconsistencies in data interpretation and analysis. Sample use case that resulted in challenge 1: A pipeline involves a feature selection step followed by a feature scaling step. If the metadata is not properly updated after feature selection, the scaling step might operate on the wrong set of features, resulting in inaccurate results. Fixes to challenge 1: The metadata router provides mechanisms to define and implement rules for updating metadata based on the transformations applied by individual pipeline stages. This ensures that the metadata remains consistent and accurate throughout the pipeline. Challenge 2: Handling metadata conflicts. When different stages of a pipeline apply transformations that affect the same metadata, conflicts can arise. For example, two different transformers might attempt to modify the same column name. Sample use case that resulted in challenge 2: A pipeline involves two transformers that both modify the same column name. One transformer renames the column and the other performs a feature scaling operation. Fixes to challenge 2: The metadata router provides mechanisms to resolve conflicts by prioritizing metadata updates based on specific rules or user-defined priorities. This ensures that the metadata remains consistent and avoids ambiguity. YAML. sklearn utils metadata routing metadata request. Description: The metadata request class is a utility class used in Scikit-learn's metadata routing system. This system allows for flexible and efficient access to metadata about different parts of a machine learning workflow, such as estimators, transformers, and datasets. The metadata request object encapsulates a request for specific metadata, including its type, source, and any additional parameters needed. Inputs: metadata type: the type of metadata requested, such as estimator type, dataset type, or transformer type. Source: the source of the metadata, such as an estimator object, a dataset object, or a transformer object. Parameters: a dictionary of parameters specific to the requested metadata. For example, the dataset type metadata might require a parameter indicating the desired data format. Outputs: metadata: the requested metadata value, which can be a string, a list, a dictionary, or any other appropriate data structure. Steps: the metadata request object is created with the desired metadata type, source, and parameters. The metadata request object is passed to the getMetadata method of the appropriate metadata router, which is responsible for handling requests for specific types of metadata. The metadata router retrieves the requested metadata from the source object and returns it to the caller. Metrics: none. Visualization plots: none. Fine-tune parameters: none. Uncertainty methods: none. Challenges and fixes. Challenge 1: metadata inconsistency. Different versions of a library might have different metadata definitions or formats. Sample use case that resulted in challenge 1: a model trained with an older version of a library might not have the same metadata as a model trained with a newer version. Fixes to challenge 1 ensure that the metadata router can handle different metadata formats and versions by providing flexible mapping and conversion mechanisms. Challenge 2: metadata availability. Not all components of a machine learning workflow may provide all types of metadata. Sample use case that resulted in challenge 2: a custom estimator might not have metadata about its hyperparameters, while a built-in estimator does. Fixes to challenge 2: implement fallback mechanisms in the metadata router to handle cases where metadata is not available or is incomplete. sklearn, utils, metadata routing, method mapping. Description: this class serves as a decorator for functions within Scikit-learn. It helps manage the metadata associated with methods, allowing for standardized processing and information sharing across the library. Inputs: function: the function that the decorator is applied to. It should typically be a method of a Scikit-learn class. Quags: additional keyword arguments passed to the initQuags method. These arguments are used to set up the metadata for the function. Outputs: decorated function: the original function decorated with metadata management capabilities. Steps: initialization: when the decorated function is called, the initQuags method is called with the provided keyword arguments. This method sets up the function's metadata, including the input and output types, the function's role in the Scikit-learn pipeline, and other relevant information. Execution: the original function is then executed. Metadata management during function execution. The checkquags method checks if the function's input arguments are compatible with the specified metadata. It also ensures that the function's output matches the declared metadata. Metadata propagation: the decorated function may modify its metadata during execution. For example, to indicate changes in the input or output types. This metadata is then automatically propagated to the next stage of the Scikit-learn pipeline. Metrics: execution time: the time taken to execute the function. Visualization plots. Flowchart: a visualization of the function's place in the Scikit-learn pipeline, illustrating the flow of data and metadata. Parameter space: a visualization of the function's parameters and their potential impact on the output. Fine-tune parameters. Input type: a string specifying the expected input type of the function. For example, array like data frame or series. Output type: a string specifying the expected output type of the function. Role: a string describing the function's role in the Scikit-learn pipeline, such as transformer, estimator, or scorer. Uncertainty methods. Confidence intervals, estimating the uncertainty in the function's output using statistical methods. Challenges and fixes. Challenge 1: ensuring that the metadata is consistently maintained across all scikit-learn components. Sample use case that resulted in challenge 1: a function may unintentionally modify its metadata, leading to inconsistencies in the pipeline. Fixes to challenge 1: the checkquarks method helps ensure metadata consistency. Challenge 2: managing metadata complexity for functions with multiple inputs and outputs. Sample use case that resulted in challenge 2: a function may have complex input and output types that are difficult to represent with simple metadata. Fixes to challenge 2: the checkquarks method allows for flexible and expressive metadata. Configuration. sklearn utils discovery. Description: the sklearn utils discovery process aims to identify and leverage the most suitable utilities provided by the scikit-learn library for a given machine learning task. These utilities can range from data preprocessing techniques to model evaluation metrics, allowing for efficient and effective data analysis and model building. Inputs. Dataset: the input dataset containing features and labels relevant to the machine learning task. Task: the specific machine learning task being addressed, such as classification, regression, clustering, or dimensionality reduction. Problem domain: understanding the specific context of the problem, including data characteristics, desired outcomes, and potential constraints. Outputs. Selected utilities: a list of relevant sklearn utilities identified for the task, including data preprocessing techniques, model selection methods, evaluation metrics, and visualization tools. Optimized pipeline: a pipeline constructed using the selected utilities, tailored to the specific task and dataset. Steps. Problem definition: clearly define the machine learning problem and its objectives, including the desired outcomes and performance metrics. Data exploration: perform exploratory data analysis to understand the dataset's characteristics, including data types, distributions, correlations, and potential outliers. Utility selection: identify and evaluate relevant sklearn utilities based on the task, data characteristics, and desired outcomes. This includes examining data preprocessing techniques, model selection methods, evaluation metrics, and visualization tools. Pipeline construction: combine the selected utilities into a pipeline, ensuring appropriate data flow and dependencies between steps. Hyperparameter tuning: optimize the pipeline's hyperparameters using techniques like grid search, random search, or Bayesian optimization to enhance model performance. Metrics. Performance metrics: evaluate the model's performance using relevant metrics such as accuracy, precision, recall, F1 score, or mean squared error, depending on the task. Time complexity: assess the computational efficiency of the pipeline, considering the time required for training, prediction, and data processing. Interpretability: evaluate the model's interpretability, considering the ease of understanding the model's decisions and the ability to explain its predictions. Visualization plots. Data distribution plots visualize the distribution of features and labels in the dataset, helping to identify potential patterns and outliers. Feature importance plots create visualizations that show the relative importance of different features in the model's predictions. Learning curves plot the model's performance against the training set size to assess overfitting and underfitting. Confusion matrices visualize the performance of classification models by showing the distribution of true and predicted labels. Fine-tune parameters. Preprocessing parameters adjust parameters for data preprocessing techniques, such as scaling, normalization, or feature selection methods. Model hyperparameters optimize hyperparameters for the chosen machine learning model, such as the number of trees in a random forest or the regularization strength in a linear model. Pipeline structure: experiment with different pipeline structures, including the order of steps and the inclusion of additional utilities, to improve performance. Uncertainty methods. Confidence intervals: calculate confidence intervals for model predictions to quantify the uncertainty associated with each prediction. Bayesian inference: use Bayesian methods to estimate the probability distribution of model parameters, providing a more nuanced understanding of uncertainty. Ensemble methods combine multiple models to reduce variance and improve prediction accuracy. Challenges and fixes. Challenge 1: data imbalance. The dataset may contain an uneven distribution of classes, leading to biased model predictions. Sample use case that resulted in challenge 1: a fraud detection dataset with a significantly smaller number of fraudulent transactions compared to legitimate transactions. Fixes to challenge 1: employ techniques such as oversampling, undersampling, or using cost-sensitive learning algorithms to address data imbalance. Challenge 2: high dimensionality. The dataset may have a large number of features, making it computationally expensive and potentially leading to overfitting. Sample use case that resulted in challenge 2: a text classification dataset with a vocabulary of millions of words. Fixes to challenge 2: use dimensionality reduction techniques like principal component analysis, PCA, or feature selection methods to reduce the number of features. Challenge 3: missing data. The dataset may have missing values, which can hinder model performance and require imputation. Sample use case that resulted in challenge 3: a medical dataset with missing values for certain patient attributes. Fixes to challenge 3: implement techniques such as mean imputation, median imputation, or more sophisticated methods like k-nearest neighbors KNN imputation to fill in missing data. Challenge 4: choosing the right utility. Determining the optimal sklearn utility for a specific task can be challenging given the wide range of available options. Sample use case that resulted in challenge 4: choosing between different feature scaling techniques for a regression task. Fixes to challenge 4: thoroughly research and compare different utilities based on their strengths, weaknesses, and suitability to the specific task and data characteristics. Experiment with various options and evaluate their impact on model performance. Challenge 5: hyperparameter tuning. Finding the optimal combination of hyperparameters can be time-consuming and computationally expensive. Sample use case that resulted in challenge 5: optimizing the number of trees and maximum depth in a random forest model. Fixes to challenge 5: utilize techniques such as grid search, random search, or Bayesian optimization to efficiently explore the hyperparameter space. Employ strategies like cross-validation to avoid overfitting during hyperparameter tuning. Sklearn, utils, discovery, estimators. Description. This function in scikit-learn helps you discover all the available estimators models and transformers within the scikit-learn library. It provides a convenient way to explore the different algorithms available and identify the right tool for your machine learning task. Inputs. None. This function doesn't take any explicit input arguments. Outputs. Estimator list: a list of tuples, where each tuple contains the following information. Estimator class, the actual class representing the estimator. Estimator name, a string representing the name of the estimator. Steps. Load estimators, the function iterates through all the modules within scikit-learn and its submodules. Identify estimator classes, it looks for classes within each module that inherit from either base estimator or transformer mixin. Create list of estimators for each identified estimator class. It creates a tuple containing the class and its name. The name is determined by the class name. Removing any leading underscores. Metrics. None, this function doesn't calculate any specific metrics. It simply provides a list of estimators. Visualization plots. None, this function doesn't create any visualizations. Fine-tune parameters. None, this function doesn't provide guidance for fine-tuning parameters. Uncertainty methods. None, this function doesn't deal with uncertainty estimation. Challenges and fixes. Challenge 1, there are some rare instances where an estimator class might not be discovered correctly due to complex module structures or inheritance hierarchies. Sample use case that resulted in challenge 1, a custom estimator defined in a separate module might not be found by all estimators if its module structure is not standard. Fixes to challenge 1, manually add the custom estimators class and name to the list generated by all estimators. Ensure your custom estimator class inherits properly from base estimator or transformer mixin. Challenge 2, the function might not be able to discover all the estimators in a complex scikit-learn project, especially if you have custom estimators. Sample use case that resulted in challenge 2, when working with a large project with a custom estimator in a separate package. All estimators might not find it. Fixes to challenge 2, extend the all estimators function by modifying its internal logic to include your custom estimators module or by directly adding it to the resulting list. Make sure your custom estimators package is correctly installed and accessible to the all estimators function. sklearn, utils, discovery, all displays. Description, this function is used to discover all available visualization displays for scikit-learn estimators. It provides a mechanism to access the different visualization plots supported by various estimators. Inputs. None. Outputs. Display names, a list of strings representing the names of the available visualization displays. Display functions, a dictionary where keys are the display names and values are the corresponding display functions. Steps. The function iterates through the registered estimators in scikit-learn. For each estimator, it checks if it has a display attribute. If the attribute exists, it extracts the available visualization displays from it. The extracted displays are then added to the output lists. Metrics. None. Visualization plots. The available visualizations depend on the specific estimator. For example, for a classification estimator, the visualizations might include confusion matrix, ROC curve, precision recall curve, feature importance. For a regression estimator, the visualizations might include residual plot, prediction vs. actual plot, feature importance, fine-tune parameters. None. Uncertainty methods. None. Challenges and fixes. None. sklearn, utils, discovery, all functions. Description, the all functions function in scikit-learn's utils, discovery module serves as a comprehensive tool for identifying all functions within a given module or package. It plays a crucial role in introspection and exploration of the scikit-learn library, facilitating the discovery and utilization of its rich set of functions for various data science and machine learning tasks. Inputs. Module. This input represents the module or package for which the function aims to retrieve all functions. It accepts a module object, enabling the function to scan through its components and extract all available functions. Outputs. Functions. This output is a list containing all the functions identified within the specified module or package. Each entry in the list represents a function object, allowing for further examination and utilization of the function's capabilities. Steps. Function retrieval. The all functions function iterates through the specified module, systematically inspecting each attribute or element. It applies a filtering mechanism to identify objects that are functions, ensuring that only valid function objects are included in the output list. Function filtering. The function utilizes a combination of checks and attributes to effectively filter out non-function objects. These checks might include verifying if the object has a call attribute, indicating its callable nature, or ensuring that it is not a built-in function or a class method. List aggregation. As the function identifies eligible functions, it appends them to a list. This list, representing a collection of all discovered functions within the input module, is returned as the output of the function. Challenges and fixes. Challenge 1. Dealing with hidden or private functions. Some functions might be intentionally hidden or marked as private within the module, using naming conventions like an underscore prefix. While these functions might be accessible, they may not be intended for public use. Sample use case. Trying to discover functions with an underscore prefix that are intended for internal usage and not documented for external use. Fixes to challenge 1. The all functions function does not specifically exclude hidden or private functions, allowing access to all functions within the module, regardless of naming conventions. This approach provides a comprehensive view of all functions, but users are encouraged to consult documentation and avoid using hidden functions unless explicitly intended. Challenge 2. Handling function decorators. Function decorators can alter the underlying structure of a function, potentially affecting its identification by the all functions function. This challenge arises when the decorated function's attributes or properties are modified by a decorator, impacting the function's detection. Sample use case. Using decorators like static method or class method that modify the function's attribute structure, potentially hindering the all functions function's ability to identify it as a function. Fixes to challenge 2. The all functions function is designed to handle function decorators by using flexible criteria for identifying functions. It relies on attributes and checks that go beyond the basic structure of a function, ensuring that decorated functions are appropriately detected and included in the output list. sklearn, utils, estimator checks. Description. The estimator checks module in Scikit-learn provides a set of tests to ensure that your custom estimators adhere to the Scikit-learn API and best practices. These tests cover various aspects of estimator functionality, ensuring consistency and reliability across different estimators. Inputs. Estimator. The custom estimator you want to test. This is typically a class that inherits from a Scikit-learn base estimator class like base estimator or one of the specific estimator classes like classifier mixin, regressor mixin, or transformer mixin. Outputs. Test results. The estimator checks module runs a series of tests on your estimator and provides detailed results, indicating any failures or inconsistencies. These results help you identify potential issues with your estimator's implementation and ensure it Meets the required standards for integration into Scikit Learn pipelines and workflows. Steps. Define the estimator first. You need to define your custom estimator class, ensuring it inherits from the appropriate Scikit Learn base estimator class. Import checkEstimator. Import the checkEstimator function from the sklearn utils estimator checks module. Run the tests. Call the checkEstimator function, passing your estimator class as the argument. This will execute a series of tests to validate the estimator's functionality. Metrics. Not applicable. The estimator checks module focuses on ensuring the correctness and adherence to the Scikit Learn API rather than providing specific metrics. However, you can use the test results to indirectly evaluate the estimator's performance, such as identifying potential issues with model fitting, prediction, and other operations. Visualization plots. Not applicable. The estimator checks module is primarily for testing the correctness of estimator implementation rather than visualizing its performance. You can use separate visualization techniques to analyze the performance of your estimator after validating its correctness using estimator checks. Fine-tune parameters. Not applicable. The estimator checks module is not designed for parameter tuning. It focuses on validating the estimator's core functionality and API compliance, not optimizing its parameters. Uncertainty methods. Not applicable. The estimator checks module focuses on the basic functionality and API compliance of the estimator rather than uncertainty quantification. You can use separate methods and techniques to analyze and quantify the uncertainty of your estimator's predictions. Challenges and fixes. Challenge 1. Missing required methods. Sample use case that resulted in challenge 1. You might forget to implement a necessary method, like fit, predict, or transform in your custom estimator. Fixes to challenge 1. Implement the missing methods correctly based on the requirements of the estimator type. Challenge 2. Incorrect method signature. Sample use case that resulted in challenge 2. The arguments or return values of your implemented methods might not match the expected signature defined in the base estimator class. Fixes to challenge 2. Review the method signature and make sure it aligns with the expected inputs and outputs defined in the base estimator class. Challenge 3. Inconsistent behavior. Sample use case that resulted in challenge 3. Your estimator might not behave consistently across different input scenarios or might produce unexpected results in edge cases. Fixes to challenge 3. Carefully test your estimator with various inputs and edge cases. Review the code and identify any potential logic errors or inconsistencies in behavior. Challenge 4. Non-standard attribute access. Sample use case that resulted in challenge 4. You might be accessing attributes of the estimator that are not standard or are not consistently defined across different estimators. Fixes to challenge 4. Use standard attributes and methods as defined in the base estimator class or in the Scikit Learn documentation for the specific estimator type. Avoid creating custom or non-standard attributes. Challenge 5. Missing documentation. Sample use case that resulted in challenge 5. Your estimator lacks proper documentation, making it difficult for others to understand and use it. Fixes to challenge 5. Write clear and comprehensive documentation for your estimator, including explanations of its parameters, methods, and expected behavior. Follow the Scikit Learn documentation style guidelines. Challenge 6. Unclear error handling. Sample use case that resulted in challenge 6. Your estimator might not handle errors gracefully, leading to unexpected crashes or unhelpful error messages. Fixes to challenge 6. Implement robust error handling mechanisms in your estimator to catch potential issues and raise meaningful exceptions with informative error messages. Challenge 7: Missing validation. Sample use case that resulted in Challenge 7: You might have omitted input validation checks in your estimator, leading to potential data errors or unexpected behavior. Fixes to Challenge 7. Implement input validation checks to ensure the data provided to your estimator is in the expected format and meets the required conditions. Challenge 8: Lack of parameter validation. Sample use case that resulted in Challenge 8: You might not have validated the provided parameters for your estimator, leading to potential errors or unexpected behavior. Fixes to Challenge 8. Implement validation checks for the parameters passed to your estimator to ensure they are within the expected ranges and types. YAML, sklearn, utils, estimator checks, checkestimator. Description. This function is a core component of Scikit-learn's testing infrastructure. It verifies that an estimator class conforms to Scikit-learn's API conventions and best practices. This ensures consistency and interoperability across different estimators. Inputs. Estimator: the estimator class to be checked. This is the central input, representing the algorithm you want to test. Outputs. None: the function does not explicitly return any values, but it performs extensive checks and raises exceptions if any inconsistencies are found. Steps. Basic checks. Verifies that the estimator inherits from the appropriate base class, e.g. base estimator, regressor mixin, classifier mixin. Checks if the estimator has the required attributes fit. Predict. Score for supervised models. Ensures the presence of getParams and setParams methods for parameter management. Data-driven checks. Tests the estimator on various data types. NumPy arrays, pandas data frames, sparse matrices SciPy. Verifies handling of different data formats, e.g. numeric, categorical. Parameter checks. Asserts the correct parameter types and values. Validates parameter consistency during fitting and prediction. Result validation. Asserts the expected shapes and types of prediction outputs. Checks that the score method provides meaningful evaluation metrics. Cross-validation checks. Ensures compatibility with Scikit-learn's cross-validation tools, e.g. crossval score. Metrics. None: the checkestimator function does not provide direct numerical metrics. It indicates success or failure through exceptions. Visualization plots. None: this function primarily focuses on functional correctness, not visualization. Fine-tune parameters. None: this function is not intended for fine-tuning parameter values. It's focused on verifying API compliance. Uncertainty methods. None: this function does not explicitly handle uncertainty quantification. Challenges and fixes. Challenge 1: Estimator missing required methods. Sample use case that resulted in Challenge 1: An estimator class is missing the fit method, which is fundamental for training the model. Fixes to Challenge 1: Implement the missing fit method. Ensure the method takes the necessary data arguments and updates the estimator's internal state. Challenge 2: Inconsistent parameter types. Sample use case that resulted in Challenge 2: An estimator expects a parameter to be an integer, but it receives a float, causing a type error. Fixes to Challenge 2: Update the estimator's parameter declaration to accept the correct data type. If necessary, implement type conversions within the estimator's methods. Challenge 3: Incorrect data shapes. Sample use case that resulted in Challenge 3: An estimator expects a 2D array as input, but receives a 1D array, leading to shape mismatch errors during fitting. Fixes to challenge 3 modify the estimator to handle different input shapes gracefully. Ensure that the data is reshaped appropriately before processing. Challenge 4 incompatible with cross-validation. Sample use case that resulted in challenge 4 an estimator's fit method modifies the input data in place, causing issues when used within cross-validation frameworks. Fixes to challenge 4 ensure the estimator does not modify the input data in place. Create copies of the data if necessary to avoid unintended side effects. sklearn, utils, estimator checks, parameterize with checks. Description. This function is a decorator that can be used to parameterize unit tests for scikit-learn estimators. It is a convenient way to ensure that your estimator passes the basic checks that are required for compatibility with scikit-learn. It uses the checkEstimator function to run a series of checks on the estimator, ensuring that it meets scikit-learn standards. Estimator class, the class of the estimator to be tested. This is the class definition of your estimator that implements the fit, predict, and other necessary methods. Checkparams, a list of check functions to run. This is a list of functions provided by scikit-learn that test specific aspects of your estimator. The default is to run all available checks. Parameterized test functions. The function returns a set of parameterized test functions that will run the specified checks on the estimator. Test results. Each parameterized test will output a Boolean value representing whether the estimator passed the specific check or not. Decorator application. You apply the parameterize with checks decorator to your test function. Check selection. The decorator identifies the checks you want to perform based on the check params. Argument. Test function creation. The decorator generates multiple parameterized test functions, each corresponding to a specific check. Test execution. Each parameterized test function runs the corresponding check on your estimator. Result reporting. The test functions report whether the checks passed or failed. Check pass-fail rate. This indicates the proportion of checks that your estimator successfully passed. Time taken to run checks. This helps you assess the performance of the check suite. Not applicable. The output of parameterize with checks is not directly visualizable. It is a tool for running checks, not for visualization. Check params. You can customize the list of checks by providing specific functions from scikit-learn's check suite. Additional arguments. You can pass additional arguments to the parameterize with checks decorator. For example, to specify a particular set of datasets or settings for the checks. Not applicable. The decorator is used to verify the correctness of an estimator's implementation, not to estimate uncertainty. Challenge 1 missing required methods. Sample use case. Your estimator might be missing a required method like fit or predict. Fixes to challenge 1 implement the missing method in your estimator class according to scikit-learn's requirements. Challenge 2 incompatible parameter values. Sample use case. Your estimator might raise an error when passed specific parameter values during the checks. Fixes to challenge 2 review the parameter values that are triggering errors and modify your estimator's logic to handle them correctly. Make sure your init method handles potential invalid parameter values. Challenge 3 incorrect data handling. Sample use case. Your estimator might not handle data correctly. For example, failing to accept sparse data or incorrectly handling data with missing values. Fixes to challenge 3 enhance your estimator to handle different data types and formats appropriately. Refer to scikit-learn documentation for guidelines on best practices for data handling. Challenge 4. Incorrect output format. Sample use case: your estimator might return outputs in an unexpected format. For example, a NumPy array instead of a pandas data frame. Fixes to challenge 4: modify your estimator's logic to return outputs in the format expected by Scikit learn. Challenge 5. Non-deterministic behavior. Sample use case: your estimator might produce different outputs on repeated runs with the same data and parameters, which can indicate the presence of randomness that's not controlled. Fixes to challenge 5: make your estimator's behavior deterministic by controlling random number generation, e.g., using a fixed seed, or by ensuring that any randomness is introduced in a predictable way. Challenge 6. Incorrect parameter validation. Sample use case: your estimator might not properly validate its parameters, potentially leading to unexpected behavior. Fixes to challenge 6: implement parameter validation checks within your estimator's init method or by using the checkparams function from scikit-learn. Challenge 7. Incorrect docstring formatting. Sample use case: your estimator's docstring might not follow scikit-learn's documentation conventions, making it difficult for others to understand how to use your estimator. Fixes to challenge 7: refer to scikit-learn's documentation style guidelines and update your estimator's docstring accordingly. Challenge 8. Missing or incorrect metadata. Sample use case: your estimator might be missing important metadata like the getParamNames method, which helps with model persistence and introspection. Fixes to challenge 8: ensure that your estimator includes all necessary metadata and that it is implemented correctly. sklearn, utils, parallel. Description. The sklearn, utils, parallel module provides tools for parallelizing computationally intensive tasks within scikit-learn. This allows for significant performance improvements, especially when dealing with large datasets or complex models. Inputs. njobs. This parameter controls the level of parallelism. It specifies the number of jobs to run in parallel. If set to -1, it uses all available processes. If set to 1, it runs sequentially. Verbose. This parameter controls the verbosity of the output. Higher values indicate more detailed logging. Outputs. Results. The results of the parallel computation, typically in the form of a list or a dictionary. Elapsed time. The total time taken for the parallel execution. Steps. Initialization. The parallel backend is initialized based on the provided njobs parameter. Task division. The input data or task is divided into smaller units that can be executed independently. Parallel execution. The subtasks are executed in parallel using the chosen backend. Result collection. The results from each parallel job are collected and aggregated. Metrics. Runtime measures the total time taken for the parallel computation. Speedup compares the execution time with a sequential implementation to assess the performance. Improvement. Visualization plots. Parallel execution timeline. A visual representation of the parallel execution, showing the start and end times of each subtask. Fine-tune parameters. Njobs. Optimizing the number of parallel jobs can significantly impact performance. Experimenting with different values is crucial for finding the optimal setting. Backend. Selecting the appropriate backend for the parallel computation can impact performance in resource utilization. Available backends include low-key, threading, and multiprocessing. Uncertainty methods. Non-parallelization typically focuses on efficiency rather than uncertainty estimation. The underlying algorithms used within the parallelized tasks might have their own uncertainty. Methods. Challenges and fixes. Challenge 1: overheads associated with parallel execution. Sample use case: running a parallelized task on a small dataset where the overhead of parallelization exceeds the gains from parallel execution. Fixes: adjust the njobs parameter to a smaller value, or switch to a sequential execution for small tasks. Challenge 2: memory limitations: running large number of parallel tasks can exceed available memory. Sample use case: parallelizing a process that requires substantial memory for each parallel job, leading to memory exhaustion. Fixes: reduce the number of parallel jobs njobs. Use memory-efficient algorithms or data structures, or utilize a machine with more memory. Challenge 3: inter-process communication overheads: communication between parallel processes can be costly, especially in distributed settings. Sample use case: frequent data exchange between processes in a distributed parallelization setup. Fixes: minimize data exchange by processing data locally or using efficient communication protocols. sklearn, utils, parallel, delayed. Description: the delayed function from Scikit learns parallel utilities is a powerful tool for parallelizing tasks within your machine learning workflows. It allows you to wrap any function with the delayed decorator, which effectively creates a task that can be executed concurrently. This is particularly useful when you have computationally expensive operations that can be executed independently. Inputs: function: the function you want to parallelize. This function can take any number of arguments. Arguments: any arguments required by the function you are wrapping. You can pass a single argument or a list of arguments. Outputs: delayed object: this object encapsulates the function and its arguments, ready to be executed in parallel. Steps: wrap your function: use the delayed decorator to wrap the function you want to execute in parallel. Create a parallel execution environment: this is done using parallel from joblib. Execute tasks: pass the list of delayed objects to the parallel instance, which will manage their execution in parallel. Metrics: execution time: you can track the time it takes to execute the tasks with and without parallelization. Speed up the ratio of execution time without parallelization to execution time with parallelization. Visualization plots: Gantt chart: this can visually represent the scheduling and execution of tasks in parallel. Fine-tune parameters: number of jobs determines the number of parallel processes. Backend controls the parallelization mechanism, e.g., threading or multiprocessing. Verbose controls the amount of output during execution. Uncertainty methods: not directly applicable. Delayed is a parallelization tool, not a method for uncertainty quantification. Challenges and fixes. Challenge 1: memory limitations when dealing with large datasets or complex computations. Parallelizing tasks can lead to memory issues if the processes consume excessive amounts of memory. Sample use case that resulted in challenge 1: processing a massive dataset with a memory-intensive function. Fixes to challenge 1: reduce memory usage in the function, optimize the function to minimize memory footprint. Increase system memory if possible. Upgrade the system's memory capacity. Chunk the data, process the data in smaller batches to reduce memory demands. Challenge 2: GIL limitations in Python. The global interpreter lock GIL limits the true parallelism of threads, while delayed can be used with the threading backend. The GIL may limit its effectiveness, especially for CPU-bound tasks. Sample use case that resulted in challenge 2: performing computationally intensive operations with threading. Fixes to challenge 2: use multiprocessing backend if your tasks are CPU-bound. Switch to the multiprocessing backend to leverage multiple cores. Consider alternative languages if true parallelism is crucial and Python's GIL is a constraint. Consider languages like C or Java that are less affected by the GIL. sklearn, utils, parallel backend. Description. The parallel backend function in scikit-learn is a powerful tool for enabling parallel processing within estimators and other functions. It allows you to specify the backend for parallel computations, such as threading, multiprocessing, or a custom backend. This can significantly speed up operations by utilizing multiple CPU cores or even multiple machines. Inputs. Backend. The backend to use for parallel computation. Common options include: threading utilizes multiple threads within a single process. Multiprocessing creates separate processes for parallel execution. Loki, a robust implementation of multiprocessing that handles object serialization more effectively. Custom backend. You can provide a custom backend object that conforms to the required interface. N jobs. The number of jobs to run in parallel. Specifying -1 will utilize all available cores. Prefer a string specifying the preferred backend. This provides a fallback mechanism if the specified backend is unavailable. Outputs. None. The function doesn't explicitly return a value. It modifies the global parallel backend settings, allowing subsequent scikit-learn operations to utilize parallelism. Steps. Set the global parallel backend. The parallel backend function modifies the global settings for parallel execution in scikit-learn. Apply backend. It configures the chosen backend to handle parallel operations. Metrics. Execution time. You can measure the time it takes for operations to complete. Comparing execution times with and without parallel processing to assess performance gains. Resource utilization. Monitor CPU usage and memory consumption to understand the resource demands of parallel execution. Visualization plots. Performance profile. Create a plot that compares execution times for different values of n jobs or different backends. Resource usage plot. Visualize CPU and memory utilization over time to identify potential bottlenecks. Fine-tune parameters. N jobs. Adjust the number of jobs to optimize performance based on the available cause and pay. Nature of the task. Prefer. Experiment with different preferred backends to find the most suitable option for your system and task. Uncertainty methods. Not applicable. This function doesn't involve uncertainty quantification. Challenges and fixes. Challenge 1. Compatibility issues with custom functions. Sample use case that resulted in challenge 1 using a custom function that doesn't handle parallel execution properly, leading to errors or unexpected behavior. Fixes to challenge 1. Ensure your custom function is designed to be thread safe or process safe. Depending on the chosen backend. Use appropriate synchronization mechanisms. Locks. Semaphores to manage shared resources. Challenge 2. Communication overhead. Sample use case that resulted in challenge 2. High communication overhead between processes or threads for large datasets, potentially negating performance gains. Fixes to challenge 2. Optimize data transfer and communication strategies, potentially by using shared memory or efficient serialization methods. Consider using a backend that minimizes communication overhead, such as Loki. Challenge 3. Memory constraints. Sample use case that resulted in challenge 3. Insufficient memory for creating multiple processes, especially when dealing with large datasets. Fixes to challenge 3. Use a backend that manages memory efficiently, such as Loki, or adjust the n jobs parameter to limit the number of processes. Consider using techniques like out-of-core processing to handle large datasets that don't fit in memory. sklearn utils register parallel backend. Description: the register parallel backend function in scikit-learn sklearn is used to configure how parallel processing is handled within the library. It allows you to specify which backend should be used for parallel execution of certain operations, such as fitting models or performing cross-validation. Inputs: backend, the name of the parallel backend to use. Common options include: threading utilizes multiple threads within a single process. Multiprocessing creates multiple processes to execute tasks concurrently. Dask, a distributed computing framework for scaling data analysis tasks. Loki, a multiprocessing-based backend that supports nested parallelism. Joblib, a library that provides parallel processing capabilities. None resets the backend to the default, which is typically threading on single-core machines and multiprocessing on multi-core machines. Outputs: none, the function does not return a value. It modifies the internal state of scikit-learn to use the specified backend for parallel computations. Steps: call sklearn utils, register parallel backend and provide the desired backend as an argument. The function updates the parallel backend attribute within scikit-learn's configuration. Subsequent operations that use parallel processing will utilize the registered backend. Metrics: execution time, measure the time taken for parallel operations, e.g., model fitting with different backends to evaluate performance gains. Resource utilization, monitor CPU or memory usage to assess how effectively backends utilize available resources. Visualization plots: performance comparison plot, create a plot comparing execution times for various backends on a specific task. Resource utilization plot, visualize CPU or memory usage over time for different backends. Fine-tune parameters: number of workers for backends like multiprocessing or Dask. Adjust the number of processes or workers used to control the degree of parallelism. Backend-specific parameters: certain backends may offer additional parameters for fine-tuning their behavior. Uncertainty methods: the register parallel backend function itself doesn't directly address uncertainty. Challenges and fixes: challenge 1, choosing the right backend. Selecting an appropriate backend depends on the specific task, available resources, and potential limitations. Sample use case for tasks involving CPU-intensive computations and limited memory. Threading might be suitable for more resource-intensive or data parallel tasks. Multiprocessing or Dask may be preferable. Fixes: carefully consider the task's requirements, hardware resources, and potential limitations, e.g., GIL in Python to select the most suitable backend. Challenge 2, overhead of parallelism. Creating and managing parallel processes can incur some overhead, which might negate the benefits of parallelism for smaller tasks. Sample use case: a small dataset where the computation time for each task is negligible might not see significant speedup from parallelism due to the overhead involved. Fixes: experiment with the number of workers or processes to find the optimal balance between parallelism and overhead. Consider using parallel processing only for tasks with a sufficient computational workload. Challenge 3, memory management. Parallel processing can increase memory usage due to multiple processes or threads accessing data. Sample use case: processing large datasets with multiple parallel processes might lead to excessive memory consumption. Fixes: carefully manage memory usage by optimizing data structures, using memory-efficient algorithms, or employing techniques like memory mapping. YAML: sklearn utils parallel. Description: the parallel class in scikit-learn's utils parallel module provides a convenient way to Parallelize computationally intensive tasks within your machine learning workflows. It allows you to distribute the workload across multiple CPU cores, or even utilize multiple machines for faster processing. This is especially beneficial for tasks like model training, cross-validation, or feature engineering, where significant computational resources can be leveraged to expedite the process. Inputs. N jobs. This parameter specifies the number of jobs to run in parallel. A value of -1 indicates that all available processes will be utilized, while a positive integer specifies the number of cores to use. Verbose controls the verbosity of the output. Setting it to 0 disables all output, while higher values increase the level of detail displayed. Backend determines the backend used for parallel execution. Options include low-key, threading, and multiprocessing, each with its own strengths and weaknesses. Prefer indicates the preferred execution method. Options include processes and threads, influencing the choice between multiprocessing and threading for the backend. Timeout sets a maximum time in seconds to wait for a job to complete. If a job exceeds the timeout, an exception is raised. Outputs. Results. A list containing the results of each task executed in parallel. Steps. The parallel class accepts a function func and a sequence of input data iterable as input. It divides the input data into chunks and assigns each chunk to a separate worker process or thread, depending on the chosen backend. The worker processes or threads execute the specified function on their assigned chunks. Upon completion, the results from all workers are gathered and returned in a list. Metrics. Execution time. The total time taken to complete the parallel execution. Speed up. The ratio of the sequential execution time to the parallel execution time. Resource utilization measures how efficiently CPU cores or other resources are being used during parallel execution. Visualization plots. Task execution timeline. A visual representation of the start and end times for each task, illustrating the overall parallel execution process. Resource utilization plot. A graph showing the percentage of CPU usage or memory consumption over time during parallel execution. Fine-tune parameters. N jobs. Experiment with different values to find the optimal number of cores to utilize, considering the available hardware resources and the computational intensity of the task. Backend. Select the most suitable backend based on the type of task and the specific requirements of your application. Prefer. Influence the backend choice by prioritizing processes or threads for better efficiency based on the task's characteristics. Timeout. Adjust the timeout value appropriately to prevent tasks from running indefinitely and causing delays. Uncertainty methods. Now, challenges and fixes. Challenge 1. Excessive memory consumption when processing large datasets. Parallel execution can lead to high memory usage, potentially causing memory errors or system instability. Sample use case that resulted in challenge 1. Parallel processing of images with complex feature extraction methods. Fixes to challenge 1. Reduce the batch size of the data being processed. Use a more efficient data representation or compression technique. Utilize a backend that supports shared memory, like low-key, to reduce memory overhead. Challenge 2. Communication overhead. The communication between worker processes or threads can introduce overhead, particularly for tasks with small amounts of computation per data point. Sample use case that resulted in challenge 2. Parallelizing a simple function that performs minor data transformations. Fixes to challenge 2. Increase the batch size of the data being processed to reduce the relative overhead of communication. Use a backend that minimizes communication overhead. like threading for tasks that are CPU bound. Optimize the data serialization and deserialization processes used for communication between workers. Challenge 3 serialization issues. Certain data types or objects may not be serializable, preventing them from being transferred between processes or threads. Sample use case that resulted in challenge 3: parallelizing a function that utilizes custom objects that are not pickable. Fixes to challenge 3: ensure that all data types used in the parallel function are serializable. Implement custom serialization and deserialization methods for non-pickable objects. Consider alternative data structures or libraries that provide better support for serialization. Challenge 4: synchronization errors when multiple processes or threads access shared resources. Synchronization issues can arise, leading to data corruption or unexpected behavior. Sample use case that resulted in challenge 4: parallel updates to a global dictionary or file. Fixes to challenge 4: utilize locks or other synchronization mechanisms to ensure exclusive access to shared resources. Implement thread-safe data structures or libraries for managing shared resources. Carefully consider the implications of parallel access to shared resources and ensure proper synchronization is implemented.